SMID, we probably need 8 times of the time. Another thing is it is can adding values at the same time instead of load. So it's well. Another thing is since we can load a lot of data at the same time to the register, so we can fully using the bandwidth of the bus. You can as bus a register may can hold only say 30 bits of data, but the bus could hold 128 bits of data. So with the SMID, we can take a benefit of the bus width. Also, it will improve the performance for if there are some same operation on on a large number of the data. And this is specifically will be speeding up the multimedia application and the 3D graphic. As you can see, so everyone played Photoshop or like similar graphic processing tool. If you're changing the lightness of all the pixels on the screen, with SMID, you can doing a lot of pixels at the same time. Then how SMID is really used. One thing that I showed in the example is we can load contiguous memory data into different registers and doing a same arithmetic operation at the same time on all the registers at the same time. Another thing is a lot of times the registers are not exactly the bandwidth of the architecture of the computer. Say we are using 6-bit architecture, but actually the register are not 64-bit. It's actually larger. So it can pack more data into a larger register, and then we can doing it contiguous at the same time. I'll show you an example later. See, here's the data. We have a register of 128 bits in the register, but we are only using 32 bits integer. So actually, one register we can load 4 integers into register and doing the SMD construction command. So we can see on the left of it's a brief example of the assembly that are doing these things. So it can be really taking advantage of bandwidth and making everything quicker because we are doing more data at the same time. Excuse me. So here is a specification of some SMID. So we have the PC starts at the Pentium MMX. I guess a lot of people are not very didn't heard of that, but Pentium, the first Pentium doesn't have SMD until I think it's like a modified version Pentium coming out. So it originally had 64 bits of register using for SMID, and it only have 8 register. So each one, the maximum it can hold is 64 bits of integer. But as you can see, if we are using normal RGB, actually 8 bits is enough for one color. So actually it can hold at least 2 pixels. Then after that, the Pentium 3 increased the bandwidth to 128 bits, which actually can using this example of the MID, which I showed, but it has 8 register. Then if we come back to the game console, PlayStation 2, even though it's just 1 year after Pentium 3, but actually it has much more register for SMID. And ARM also having its own SMID architecture, but it's optional. And then we can see on 2006 PlayStation 3, it has incredibly number of SMID, which is 128 SMID register. But actually, right now, even from Pentium 4, it only have 16 register number. So it said the more requirements on the graphic processing, the more SMID it is for the architecture to be implemented. Then how we are using SMID during code. For sure, we can write assembly because SMID is architecture, so you can using that directly using the CPU code. So I have an example is in ARM, it has a VAdd compared with normal add, VLoad compared with normal load, but it's really hard to use. Another one is called intrinsic. It's kind of a shortcut. You can directly using into C and using the assembly function. Or you can use in vector class, which is also an example for use how you would using the SMID. If you put everything as a vector, it will be in default using this. Why there is something called sound? Can I cancel it? Sorry, the screen.
Yeah, you could cancel it. A couple people were having problems hearing, so I'm just polling. You can cancel it.
I just cannot see my mouse. All right, I probably has to, let me keep going. Okay, so then another one is a normal, is the one that most recommended is we just using, when we're compiling the code, we asking the compiler to doing as much as possible to compile it into the way to utilizing the SIMD. So we can having a flag into during the compiling. Here is I stealed from Intel architecture. It has kind of recommendation for what is the way to using SMID when you are using Intel CPU. So here is a thing that is most recommended to using vectorizer of Intel and in this compiler. So, but there are still some other disadvantages in SMID. One is it's not all algorithms can easily benefit from SMD, and also has a larger register file. Which register file consume more power and requires human involved to implement SMID at the instruction level, and it also needs a bunch of optimization based on what the program you're using and how you're using the program. And then at the beginning, supercomputer using that, then PC finally adopted because of the graphic needs. And now even web has its own way to implementing SMID on the code level and the compiler level. So some of the application in future is encrypt and the parallel memory access on the GPU because there are lots of memories on GPU. And also we have a future, or right now we have single instruction on multiple thread, which is a further concept from SID. So that's all my presentation, and that's a part. I think that's part of the architecture benefits for people to see. Thank you. So I try to squeeze into 10 minutes. It's on.
Yep. Nope. Your time was good.
I have a question here.
Yeah.
So what are the algorithms supported by this SIMD?
So let me show you this example. So you can see there is one thing people call the vector, or you can think it's array. Anything can be packed into array, and you are operating the same thing on the array, it will benefit from SIMD in natural. But of course, there are different things. For instance, if you think about you have a graphic, you have a picture, and you are rotating it. The rotation, technically, you cannot directly apply the SMID on it, but there are algorithms can converting the rotation into the way that into the vectorized way, then it will be applied the SMID. So that's why it needs optimization. Sometimes not directly using SMD, you have to think about how you can.
Okay.
Is that answer acceptable?
Yeah, I think I know few algorithms which support that kind of process, so I got an idea of that. And
technically in compiler, it's very hard, but if the optimization sometimes they know that a bunch of, they can put in everything, scan in the memory and see, oh, here's thing, here those things are doing the same thing at this time, then putting them together into the register of SIMD, then put it back. So if you can find out the memory doing the same thing, you can always put it together.
Yep.
So SIMD is a very common thing in computer now, like any CPU has it.
All right, anything else? All right, good job.
Okay.
I'll clap. All right. Next volunteer. Don't all jump at once. All right, Karan, you're up. Let's see. Is he here?
Apparently he is here.
Hello.
Oh, hello.
Yeah, 1 second. Yeah. Hello. Everybody can see?
Yep.
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 Yes.
Now I can't see. 1 second.
Camila said she's having connection issues. She's restarting the modem or something like that.
Mr. Gonzalez actually kicked her off.
That might happen to
Yes.
me at some point too.
See if he does have a button for kicking people off. He does. Here's a little button that says remove.
Yeah. Everybody can see?
Yes.
Yeah. Okay, then should I start?
Yep, you're good to go.
Okay. So yeah, my topic is computer infrastructure and cloud computing. Yeah, one. Yeah, the component of infrastructure. Let me talk to you about the infrastructure first. The term computer infrastructure is defined in information technology infrastructure library as a combined set of hardware, software, and network facility. The second component is switching is device that provide connectivity between network and a local area network. The third component is router. They move the package to the network. Router allows device separately on different lanes to talk to each other by determining next stop, and they eventually send the packages to the right destination. The last component of infrastructure is firewall. Firewall are the security device at edge of the network. The firewall is the guardian and a protector from the he can create rules, and we can protect our protocol for traffic from one device to another device. Now we will learn about the internet infrastructure. Internet infrastructure is a global connection of internet, both big and small. This network internet connection is made different ways from single to entity that we know as internet. Every computer connect to internet is part of network. Even if we are at home, for example, we are connected at a modem or a dial, we are connected to the main internet service provider, INS. At work, for example, at we are at a work, but most commonly we use the workplace IP ISP, and that company has contracted with the ISP provider, then we connect by their network. This is how we connect, like from home and from some business place also. It's not like in business the computers are connected in lane, and we are connecting to the router, but there is a part that connect through a POP, post office protocol. It's called as post office protocol, and then it goes to NAP. It's the network access point, and then the main we can it shows to ISP, internet server, then we can access the internet that way. Now I like to talk about the cloud computing. The cloud computing is the delivery of demand computing service from application to storage and processing power, typically over the internet and pay as you need it. Rather than owing, now the companies, they are in tight of budget, and if they are a new startup and they are like a little tight on budget, so the cloud computing is the basic need of all service providers. Computing service cover vast range of options now, from basic storage, networking, processing power through natural language processing, and artificial intelligence. These time sharing services are largely overtaken by the risk of PC, which made owning a computer much more affordable, and then it's turned by rise of copyright data, which company will use store, and they can store vast amount of data. The cloud computing containing applications, they can monitor, they can contact, collaboration, communication, finance. The platform, they can use object storage, identification, runtime, queue, database. Then the infrastructure is like compute, like storage and network. The reason to use cloud computing is like better security management. We can, if the data is being stored in a cloud, it is possible that it is more secure than we can store in our computer or our database. Using a latest software technology that ensure that your data is being stored in right cloud position, and there is a remotely accessible data that in-house, if we need any data, the IT team can quickly wipe it out, the sensitive data, if machine falls into wrong hand. The manage cloud, to manage cloud service provider, ensure that information stored on there is a virtual data center, and it's safe and accessible to authorized parties only. The companies, they are if there is some problem on cloud phase, they have another call, they have like they have disk space. Oh, sorry. They have a backup of the data that can be used remotely to the server, and we can use via computing. In case of disk space isn't a factor, by making the right choice, you can gain practically. There are unlimited storage on managing backup solution. The future of cloud computing is like research now. Nowadays the cloud computing will transfer even aspect of business and logistic customers. Globally, there are 47% of survey participants said that their companies using IT infrastructure already are public or private cloud computing. Cloud computing helps the business to focus and improving the efficiency of fasting innovation. Over the next decade, the cloud will be the continue to evolve as a part of a technology. Now we can see that cloud computing has, as of like it's a little survey that we can see that it's like survey revenue. The dark blue one is IaaS. It's like infrastructure as a service. The orange one is infrastructure SaaS. So it's like for software as a service. And the green one is PaaS. So it's platform as a service. This is the graph that the company from all over the world is using on cloud computing as a platform. And the number one is Brazil. Thank you. Any questions? Hello.
All right. Any
I
questions?
got a question.
Yeah.
So why did you choose cloud computing to do research on?
Like it was, the topic was computer infrastructure, and I was investigating on infrastructure. I researched on infrastructure, but there was like a vast topic. So the one topic is like cloud computing of that. As
So like, why exactly that cloud computing? Why did that kind of strike something with you? What did you find
because I was finding the internet infrastructure. From there I connect the cloud computing. Yeah.
Okay.
Any other questions?
Anything else? I just clicked the clap reaction. Did anything happen on anybody else's screen? What happens when?
It does, yeah. It makes a clap.
Oh,
Really?
does
I
it?
didn't
Like,
hear anything.
Look at the
Yeah.
videos or the picture tiles.
Yeah, the
Sorry, look at the cameras. I don't know what you call these.
What?
Look at me.
oh, I see. I see. Look at that.
Look at me. I'm clapping. See?
I clap first.
Thumbs up.
I definitely don't see anything.
I don't see anything either.
You got to look at the like the grid of everybody's like video feeds.
You
I'm
must be
doing
new.
that.
Yeah, I'm doing that.
All right, hold on. I'm about to clap right now. Boom.
I saw nothing.
All right, hold on.
What do you
hold on.
guys see?
Mr. Gonzalez is going to clap.
So amazing, Ani. So amazing.
Clapped. I don't know what you guys see.
I don't know either, Ani. I'm with you.
Me neither.
Whatever.
I'm glad Gonzalez could join us tonight, though.
I know. He was excited.
Can I go next before my internet fall again?
Sure.
Go for
Can I
it.
go after Camila?
Go for it.
No.
Please?
Wait, what are you eating? What are you eating? Doritos?
I found this.
Crunchy
Oh.
cheese bite.
Oh my goodness,
Sounds
this is
so
so
good.
good.
So Wisconsin.
I'm addicted. And it's almost healthy.
Okay. Can everyone hear me?
Yep.
Hearing
And we
you.
can see your screen.
Okay,
Yeah.
good.
Yep.
All right. Let me start my timer. So today I decided to go risky and talk about mainframes. How many of you guys ever seen a mainframe before? Okay.
Me?
Yeah, today I just oh,
Me.
you have? Cool. Today I just requested a tour through a mainframe because I'm really curious about how they look like. The story, the definitions and use, the cost, infrastructure, language used in mainframes, and the future of mainframes. So mainframes, the first mainframes started being developed in 1930s, and the machine was not ready until 1943. So it took like 13 years to create one, and it weighed 5 tons, filled an entire room, and cost about $200,000 back there to build, which today is like 28 millions of dollars. So it was very expensive. And however, IBM on the 60s, just to clarify, all my articles was from IBM. I could not find anything, any other material outside that was valuable as IBM had. So just because they're the biggest ones on the market. But on the 60s, they started to change the course of computers when they began to standardize the hardware and software that they offer to customers, because by having standardized mainframe computers to run their workloads, customers could write business applications that they need the specializations regards to hardware to make that happen. They also develop a way to have more than one workstation connected to it, so that completely changed how people start using it, because mainframes is very centralized when it comes to have it in a company. And but what is a mainframe? A mainframe is just a style of computer, and it is capable of processing a bigger amount of data because of its infrastructure. And it's basically a large central computer with more memory, more storages, and processing power bigger than we can have in our machines or even in a common server that we have. And what is it used for? Who understand the term critical applications here in a company? What would be a critical applications? Okay, yeah. So a critical applications is any software that's developed inside a company that can't be tolerated any time down, because that application makes helps the company makes a lot of money and control a lot of data around the company, so that can't really be down for a while. So most of these critical applications that's developed for the companies are run on mainframes. Not because mainframes are like supercomputers, nothing like that. It's mostly because mainframes are able to process more simple applications and that have a huge amount of data coming in. And that's basically what a critical application is going to do on the front end for their customers. They also can have a build data processing, such sensors, industry data and consumer statistics. It usually runs enterprise resource planning. I don't know if you guys have ever developed enterprise resource planning or have worked with one, but it usually has different modules inside a company, and that software is capable of having company entire databases. And from that, you can have a view of how the company does just by putting those modules together that belongs for different departments. Bank transaction process, that's the biggest one, because I think 93% of the banks today is still using mainframes. So if today you went to an ATM, you had a indirect connection with a mainframe. And next here is how much it actually costs. So surprisingly, I figured out that IBM decided to invest more and more in mainframes. And they made the latest one, the Z Enterprise, 25% cheaper than the previous version. So you can have a mainframe at your door today for only $75,000. And the ZOS system, for example, it can holds up to 232 servers. I'm going to explain where the server later. And however, there is software license and contracts that you need to consider when you're buying something like this. And that does not mean that you bought a ZOS and it came with 232 servers. It just means that you bought a box capable of having 232 servers. And I wanted to clarify that. Can you guys still hear me?
Yeah, I can still hear you.
Yes, I can hear you.
Is anyone hearing? Okay,
Yep.
all right. Sorry, I had a message here. So infrastructure. This is, I think that was the simplest way that I could define how is the infrastructure of a mainframe here. And these are outpars. That's how I usually call on my daily work, outpars. So outpars is usually where we are calling servers, instances, or it's basically the part of the mainframe that is going to run the OS. Okay, so we can compare it to a memory, or that's what I could bring closer here today. And they also have processors, a bunch of processors, because it can connect. When you have outpar, for example, you usually will need to define how many processors you use and how many stars it's going to take, because it's going to be able to process X amount of business applications, for example. And the channels are the part that provides I/O. So between those parts, those hardware parts, they have the system control. For example, a system control will have something like a system assistant processor that's gonna usually make the connection between the channels and the processor and be able to process a huge amount of data. And that's basically how that would work. And just a reminder that one box can have up to 260 60 servers, outpars only. So if you have, if you want to have more than 60, you have to buy another one, which if you want to use the max with 232, you're going to spend at least $280,000 just to have this box in your door. And you can use different languages. You can work with assembler, COBOL, C, C++, Java, Perl, Rex, all these other languages. The most common one, especially for banks, are COBOL. But just to remember that each of these boxes can have a different OS running on it. So even if you make assemblers for this machine here and assembler for this one, and these machines have different configurations, in the end, it's going to be hard for you to make that data to connect. So you got to be careful when you are making a mainframe. So the future is very clear. People are using more and more business applications. So companies is going to have more needs to mainframes. And it's expected to be to have 93% of the big companies in the world using it, and it will grow 4.3% by 2025. And my conclusion is that dinosaurs ruled Earth for 145 million of years, and I believe that mainframes is going to stay on the same path because we need it. IBM is making sure to make that every day more standardized for what technology is and more accessible for companies and very exclusive for data, especially for data science. Any question?
Yes, I have.
Yep.
So my question is, Karan just introduced the cloud computing, and more financial companies moving to cloud rather than use their own hardware. Then does dinosaur will be distinct soon?
No. So what they say is that I did read an article on that. What they say is that even with the cloud computing, the mainframe is still needed, even to base the amount of data that goes through cloud computing that's somewhere. And it's not like it is a supercomputer, as I said before, but it will not gonna change. Even because if realistically speaking, on the business today, a company is not gonna go 100% on a cloud. They're gonna still having a lot of its data on on-prem, because number one, most of these companies are concerned about safety, and second, because they had like 20 years of investments on prem, and go to cloud is a real risk, especially when you have risk management inside the company and other stuff too. Does that explain a little bit?
Yes, but I just a little curious.
Yeah.
So what's the trend? More companies using mainframe or more companies using cloud?
More both. I think it's gonna be both, because the same amount of companies that go to mainframe and go to cloud, it's raising the amount of people that are developing applications, specific applications to companies, and they have the need of having those applications run on mainframe, because even mainframes being expensive today, it 93% of the big companies use it, but it only corresponds for 6.3% of what IT actually spends with it. So it's a cheap way to produce a amount of data, keep it safe because it's safer than other servers, and keep that going, even because of the amount of process that it's able to. So I believe that the future is to use more and more IBM's frames because they are more accessible.
Okay, thank you.
Yeah, just want to share one more thing. As I worked in IBM, so IBM will mainly concentrate on mainframes for banking sector, government applications, and pharmacy. So these things, mainframes will still be there.
Yeah. Yeah, so here, just as a curiosity, I brought a picture of how a mainframe OS look like.
AS400, yes.
Yeah, this is an old picture, but I have a link here that I'm going to share with you guys how the new mainframes looks like, which is beautiful. It's just like a Tesla. I'm serious. Any other questions?
I don't have a question, but just a comment. I thought that was really interesting how you were talking about how expensive it is to have the mainframe, but how so many companies still have it, because that's exactly what's going on at Acuity right now and has been for many years, is that we're spending a lot of money on our mainframe, but there's no way that we can really get rid of it.
Yeah.
So, I don't know.
Yeah, and other things too, that there's just a little people that are able to work with mainframes on the market today. So these companies are looking more and more for people that are specialized on that. They find a lot of people that are specialized to develop on mainframes in India, but they don't find many here in the United States. That's what I'm seeing.
And one more company which works on mainframes mostly is Infosys.
Infosys, okay, yeah. I did not know that. All my articles was from IBM because they are
Yeah,
the
I know.
biggest one. Yeah.
True.
Yeah,
we're an IBM shop at Acuity.
Yeah, my wife works as a COBOL programmer at Western Illinois University, where I used to teach. So she sits there and stares at that screen like that all day, every day.
Yeah,
I just now they're starting to think about replacing it, so they're starting to move towards a newer product, but it's going to be a long transition because they're having to invest a lot of money to move to a newer technology because of the amount of stuff they've built on the older technology.
Are they a banner school?
Not yet.
Or is that where they're going?
They're not going to Banner. They're going to something, you know.
Workday?
I don't remember the name. It's not that either. I don't remember the name of it. Unify? Unify.
I haven't heard of that one.
Yeah,
I
I
have
think
those
it's
commands how to log into those AS400 servers.
yeah, I think it's some like startup one that they're just working together with the school to turn it into something. Who knows?
Yeah, that'll probably be a years-long process for them.
Yeah, my wife's hoping to retire before it's done.
Cool. Yeah, any other questions?
So does anybody know what the difference is between running a mainframe versus running a virtual hypervisor environment, like VMware or something like that?
Yes. Actually, mainframe is built on different OS, so it doesn't support any virtual support. But we have virtual servers which we use separately instead of virtual box or virtual machine. We have servers in which they provide us. So using that, we can log in. They have dedicated IPs for that.
So you can run various virtual machines on a mainframe?
We can run through our laptops to log into that mainframe servers. If you want, I can show that I have those servers list when I worked in IBM.
I think what Eric's asking is, can you actually use a mainframe to spawn like Linux virtual machines that people can use as if they were running on their own individual computers? You know, because one of the things with mainframes is they are a centralized computer with lots of resources. So usually in computing, when we think about a centralized computer that has a lot of resources, we might want to divide those resources up among multiple virtualized computers. So am I right here in that, Eric, you're asking, is that a use case for a mainframe?
I think there's no such option like we can use that in that cases.
I haven't seen either. I know that you can have different workstations that you're gonna create. That's why we have like so many credit cards being passed. But I haven't seen like virtualizations of it's. I even put it here if I had time to show. But even when we map that through the network, it mapped. It has like a box, then have the ALPAR, and that goes straight to the instance that's generated to run an application, but I haven't seen it generating the virtual machines itself. I have seen they have MQs between the ALPAR and an instance, but I don't think that would be considered a virtualization. I'm not sure.
I think it is. I just am looking at the article here. IBM actually made up the hypervisor, which is how virtualization works, and LPAR is an outgrowth of that. I think it's a different implementation than what we use with VMware.
I think
it's a related technology.
That's for AIXOS, I guess.
Mm-hmm.
Yeah, it's interesting.
Yeah, the technology I work with can be run off a mainframe, or it can be run off of a virtualized Linux box. And I'm on a listserv, and I hear a lot of people talking about AIX, which is a Unix distribution that runs on mainframes. And
yeah, I got it.
like
I worked on that too.
Camilla was saying, it's a very specialized thing. When they ask questions, I'm like, I have no idea. Good luck. So.
All right, anything else? All right, let's keep, somebody else?
Yeah, actually, we used to log into those mainframe servers using virtual machine consoles. So few servers are there, such servers.
All right, and so Priscilla, you said you wanted to go next?
Yes, can I?
No.
Please.
All right. The answer's still no.
Camila, can you stop sharing your screen, please? Camila.
Mila.
think she's froze.
Here.
Dr. Lippman could free her up.
Stuck.
Yeah, I could do it. Hold on.
Can you guys see my presentation?
Yes.
Yes.
Oh, wait a minute. I have to. So, can I start?
Yep.
Today, I will talk about big data architecture. What is big data? Big data, it's known as a huge volume of data that cannot be stored and processed using the traditional approach. When you think about big data, I think everybody thinks about just the volume of data, but it's not just that. If you think how much data is considered big data, the answer is it depends. Depends on the application, depends on what it's being used for. For example, a simple email with 100 megabytes can be considered big data if you cannot attach an email and send it. So because of the application, it can also be considered big data. 10 terabytes of image files that need to be processed and resized. And for example, if the image needs to be enhanced in a certain time frame, usually a regular computer will not be able to complete this task as quick as other kinds of applications. So it can also be considered big data. But as I said, it's not about just the volume of data. There are these 4 V's that determine if a data is considered big data or not. And as I said, the volume, the scale of data is considered, but also the variety of data. For example, nowadays we have data from social media, we have images, we have audio, we have all kinds of format of data. And all of those aligned with the volume and the scale of data that we generate every day is also considered big data. The velocity that we stream this data is also a factor to be considered big data. So how mostly with the Internet of Things, every second we are creating data, and how fast we need to access this data is also very important. So for example, cars sensors, we have to have a very quick response. For even GPS response, we need to know when you're accessing a GPS, you need to know if there is traffic or if there is something that you should be aware. This data has to come to you very fast, so it's also considered big data. And also the veracity, if this data is trustful, it's another factor to determine what big data is. So there are some big data solutions workload. So what is big data is used for? And one of them is batch processing. Batch processing is a technique in which an operating system collects the programs and data together in a batch before processing starts. So it's actually grouped in batches to be processed easier. Real-time processing of big data in motion. As I said about velocity, the same way that we receive data in a huge volume and we need to have response really quick. So analyze massive quantities of information instantaneously without delay. Data in rest loses its value exponentially over time, thus make it not as effective as data in motion, which requires real-time processing. So for example, if you are searching on your phone on Google, you're looking for like gym near me. It's a search that I think I do once in a while. It's important that this data is shared for, looking for the advertising purpose. So I'm sure it happened with most of you. You're searching something on Google and then instantaneously, you have a Facebook ad about the same thing. So then you have a Facebook ad about gyms that are around you. This ad needs to coordinate with the timing that you're searching for this gym on your phone. Otherwise, it doesn't make the same effect if you receive the ad 3 months after you start your searching for a new gym, for example. So timing is very important too. Interactive exploration of big data. For example, if you have if you're an Uber driver and you have your Uber app, you are updating, data is being updated in real time. And the way that the pricing for the rides works, if you have more drivers in a certain area, the price of the rides will drop. If you have less drivers in the area, the price of the ride will raise. So those are interactive explorations of big data. You need those data needs to be updated in real time to be effective. Predictive analytics and machine learning. Machine learning is the process of teaching computers without the intervention of human beings. So we teach the computer to think like us, and for that we need a huge amount of data so they can analyze the regression of this data and then make better decisions. And as much data you have, more accurate your predictions are. So for big data architecture, big data architecture is the foundation for big data analytics. Architects begin by understanding the goals and objectives of building a project. So the architects needs to talk with the stakeholders, understand exactly where they want to, what they need, and then do all the planning to where and how they want to achieve these goals. So there are some types of workloads for data architecture. Data source. So all big data solutions start with one or more data sources. They can be relational database, web servers, log files, real-time data sources, and all data that comes from the Internet of Things. Data storage. So the data for batch processing operation is typically stored in a distributed file store that can hold high volume of large files in so many formats, different formats. Real-time message ingestion, if the solution includes real-time sources, as I mentioned before, The architecture might include ways to capture and store real-time messages. Batch processing, I already talked about that, how the processes grouped in batches, so the processing is easier. And stream processing. After capturing the real-time messages, the solution must process them by filtering, aggregating, and otherwise preparing the data for analysis in general. And then the analytical data store. Many big data solutions prepare data for analysis and then serve the processed data in a structured format that can be acquired using analytical tools. The analytical tools can be any tool that will work with even relational database or business intelligence tools. And I will also talk about data lake, which is a storage repository, a large amount of structured, semi-structured, and unstructured data. It is a place to store every type of data in its native format, so without processing. We can have in the same place images, audio, log files, everything. Since it's not structured, it's easier to be modeled and restructured if needed before being accessed. The difference between data lakes and data warehouses, data lakes has raw data. Data warehouse has processed data. So all the rows and columns already indexed, so a regular database that we know. The users for data lake database, they are usually data scientists because it needs a little bit more technical skills to access this data. But from data house, any business professional can access data from there. Anyone has any question?
Any questions?
Sorry, guys, I tried to don't go over my 10 minutes. I think I was too much.
I'll give you the 11-minute cutoff perfect. So we'll call it no time penalty, but right at the edge.
Oh my goodness. Yeah, I had my penalty last time and it really hurts.
All right,
so we
questions?
have to be great in 10 minutes, but less than 11. Is that the rule?
Well, I would say no penalty will be given for anything that's 9 minutes and 59 seconds up until, I would say safety is between 9 and 11 minutes. You're safe in that range. So 1 minute of grace period on either side.
Okay.
There's so much to talk about big data. It's just so hard to do in 10 minutes.
That's right, but everything can't be most important. Gotta decide what's the most important stuff.
Yep.
So nobody has a question on big data?
Why'd you pick the topic?
Why? It's a topic that I'm very interested in. I work with data analysis, and from the last part of the architecture, which is the analysis and reporting, this is the part that I work with. And since data lake is something that I'm very interested in learning more about, so this was actually I picked this topic because of data lake.
So do you feel like after doing your research outside of your work that you have a better understanding of what you're doing as far as work? Yeah.
Yeah, definitely. Mostly for data lake. I feel like I read a bunch of articles specifically about data lake, and I definitely understand more. I don't use data lake at work, but if I need one day, Yes, I understand better.
So can I ask a question?
Sure.
When you are mentioning the data lake, so can you make an example for, say, implemented the data lake, say by either a company or by someone?
So when you think about for data lake, you can think there are a couple tools that you use from different brands, but basically you have can you imagine like a computer folder, like a folder in your computer where you just toss everything there. You don't structure anything. Actually, a folder will structure even images or audios because they will classify by date, there's modified size, but just the idea of having a folder and tossing all the information there. And when they need to be accessed, you go straight to that information. You don't need to map or go over everything. And then you can use this, whatever information you need from this database, you can grab there, and then you format, and then you structure, and then you put on a table or any other regular.
So does that actually data lake means raw data not being processed or categorized?
Yes, it's data that is exactly data that is not processed, it's not categorized, it's not standardized, it's all kinds of data there. And since we have a huge volume of data every day, mostly for the Internet of Things, you have data every second, a huge amount of data every second, and all this data, it's easier to just toss this data in some place, and when you need to access, and then you look for it. You don't organize, you don't waste time or resource processing before storage. You just process after storage.
Thank you.
Anything else? All right. Who's next?
I can go next.
All right.
Let me just turn off the dryer really quick so that you don't get background noise.
Mm-hmm.
Hopefully that's a little bit better. All right. Trying to see if I can open up the PowerPoint twice so I can see my notes. Is that something you could do?
If it's with PowerPoint, I think there's a way to show PowerPoint where your notes are up on the screen, but for presentation mode. But then since you're sharing your screen, I bet you we would probably see your notes, but that's okay.
Let me see. If I can figure it out.
Are you only operating off of one screen?
I got a monitor.
So you should be able to open up the PowerPoint in presentation mode.
Oh yeah, I see.
Shove it onto the other monitor and you can share that screen with us.
Okay. All right. See, my embedded systems in robotics slide.
Yep.
Sweet. All right, so not sure what that is. So the reason that I kind of landed on this topic was I kind of started off, I wanted to do a presentation on Mars rover and the infrastructure and architecture involved with the Mars rover. And it obviously didn't work out like that. There wasn't a whole lot of information that I could find online on how the Mars rover works. And the information that I did find, I couldn't understand it. That kind of spiraled into what is embedded systems in robotics. So basically, what is an embedded system? How does it work in robots? So let's go to the next slide. So what is an embedded system? It's a small computer on a single integrated chip used to solve a specific problem. So an embedded system is the integral part of a large system with hardware and mechanical parts that's purpose is to perform a specific job. Today, embedded systems are found in almost every electronic device we are using in day-to-day life. Some common examples are video games, smartphones, washing machines, microwaves, and so on. Any device that measures, stores, controls, calculates, or displays information must have an embedded system inside. So, there's two types of embedded, or most common embedded systems have either a microprocessor or a microcontroller. So in this slide, I'm kind of going over the difference between the two. So a microprocessor doesn't have memory, peripheral interface circuits, and other components. It needs to be connected externally to a power, so like the power consumption is pretty high. It is used in more complex big systems. And also the designing and hardware cost is high, so it's not very easily to replace. So that would be the picture at the very top, what a microprocessor is, versus a microcontroller is used to execute a single task within an application, has all of the components, like the CPU, the memory, RAM, ROM, input, output ports, timers, etc. It has reduced power consumption, size, and cost, and thus is easy to replace. So it's kind of like two sides of the extreme. So the most common in robots is actually going to be the microcontroller. So we're going to kind of focus on that. So one of the most common microcontrollers that exists in robots is the 8051 microcontroller. It was designed by Intel in 1981. The features of the 8051 microcontrollers, it has a data bus 8-bit and address bus 16, RAM 128 bytes, 32 general purpose registers, each of 8 bits, a 16-bit program counter, and data pointer. So kind of looking at the image here, the system bus connects all of the support devices to the CPU. The system bus consists of an 8-bit data bus, 16-bit address bus, and bus control signals. All other devices like program memory, ports, data memory, serial interface, interrupt control, timers, and the CPU are all interfaced together through the system bus. So here I have a kind of, this actually looks really familiar, doesn't it? To our Arduino. It's like, look at that. We were just working on the sensor right here. So I use this picture because this is actually utilizing a microcontroller in 8051. So this is a picture of an obstacle avoidance robotic vehicle. It's designed to detect and avoid the obstacles on the robot's path. For this purpose, an ultrasonic sensor pair is used, which is interfaced to the microcontroller. So just the sensor that we were just working with last week, basically, paired with the microcontroller. And if any obstacle is sensed by the ultrasonic sensor, then a signal is given to the microcontroller, which is in turn generates an appropriate output signal. So how it works, the microcontroller 8051 consists of 4 input-output ports. Each port consists of 8 pins, which are configured as input-outputs based on the logic state. So when you're thinking like of the Arduino, just that one chip, it basically looks like the same thing, where it has all those pins sticking out of it, right? Like, or all the ports. So how the microcontroller works, if logic is 0 is applied to the appropriate input-output bits, then the microcontroller pin acts as an output pin, and there will be a 0 voltage at the appropriate pin. So this sounds a little bit familiar, right? Kind of how we were working with the light bulbs at the very beginning, where if you give it a 0, it doesn't light up. You give it a 1, it lights up. Similarly, if the logic is a 1, is applied to the appropriate input-output port bits, then the microcontroller pin acts as an input pin, and there will be a 5-volt voltage at the appropriate pin. So if any obstacle is sensed, I think I said this. Oh no. So if any obstacle is sensed by the ultrasonic sensor, then a signal is given to the microcontroller, which is in turn generates an appropriate output signal. The output signal is fed to motor driver IC, which is interfaced to the motors of the robotic vehicle. Thus, based on the signal received from the motor driver IC, the motors can change the direction, so left, right, forward, backward, and of the robotic vehicle to avoid the obstacles if they detect any by the ultrasonic sensor. So I thought that was kind of cool. So this next slide, this is actually an Arduino and an 8051 microcontroller. I actually found a website that gives you directions on how to build one. So if you guys are interested, I can shoot you that link. So all you really need is the microcontroller and then pretty much like the wheels, this like base, and then we pretty much have everything else. You probably recognize some of the stuff. So there's a sensor in the front, and then you got some, it looks like female to male ports. Yeah, that's the board right there. So you pretty much got all your stuff that you need. So if you want to build one, I can send you that link. Just let me know. And to top it all off, I got hippo attacking an alligator. Isn't that wonderful?
I do like that.
It is wonderful.
That, yeah, she asked me what my opinion was, but I told her that I wanted to be surprised.
So I picked a scary animal, which is a hippo, with another scary animal, which is an alligator.
So the question is which of those animals do you think is actually more dangerous to humans?
I think hippos win.
Yeah.
I'm pretty sure.
Well, not just win. Hippos are like incredibly territorial. Mm-hmm. Like more hippos kill humans every year than crocodiles kill humans by like a huge margin.
I believe it.
Yeah, no, they're awesome. Mr. Gonzalez wants to get a hippo, but Tabby won't let him.
Does anybody have any questions for me?
Nope.
Cool.
Okay, who wants to go next?
Can I go next?
Sure.
Okay. Share screen. Oh my God. So can you see my screen?
Yeah, I can see it.
Yep.
Okay. So let's start. I wanted to talk about the IBM True Not chip, which is built by IBM. Okay. So What is true not chip? Basically, it is brain inspired from the brain structure. IBM developed a neurosynaptic chip which works similar as the animal's brain. Computers and brains work in virtually opposite ways. Computers are laboriously programmed for a specific task, while neurosynaptic chips work like animal brains. Brains learn from experience and can perform a wide a variety of complicated tasks that are currently impossible for a computer. So talking about the components in this chip, is the chip contains uh, 1 million programmable neurons and 256 million programmable synapses. Basically, synapses are the building blocks or the connection between two neurons across 4096 uh, individual neurosynaptic cores. Not only this, it is built on Samsung 28 nano Samsung's processor, and with a monstrous transistor count of 5.4 billion. This is one of the largest and most advanced computer chips ever made. So, and it has uh, over 400 million of local on-chip memory cells to store the synapses and the neuron parameters. Talking about the efficiency of this chip is like, yeah. So True North is the first to achieve 770 megawatt total power while running a typical recurrent network at biological real time, 4 orders of magnitude lower than a conventional computer running the same network. Multi-object detection and classification application with 240 by 400 pixels, 3-color video input at 30 frames per second. The chip consumes only 65 megawatts. Not only this, also the synaptic events, which is the lowest recorded energy for any large-scale neuromorphic system, and 5 orders of magnitude lower than von Neumann's computer. That basically it is an architecture that is followed in the modern day computers. 20 megawatt per centimeter square power density, which is comparable to Cortex, but is 3 to 4 orders of magnitude lower compared to 50 to 100 watts for a CPU. It is 30 times less area per neuron than the previous approaches that were like uh, in the analog or different computers. Scalability. True North is the first chip to achieve design scale down to uh, 28 nms. Fully digital design scales down even further to smaller feature processes, and scaling capability to 1 billion neurons and 256 billion synapses with a power consumption similar to a desktop computer or something like that. Okay. So for the design, True North has a fully event-driven digital mixed synchronous and asynchronous neuromorphic architecture. This reduces neuron switching by 99% on average for a typical network. Asynchronous routing network for 4096 cores with low latency spike delivery at 0.3 per bit UMs. Complete synchronous and asynchronous design and verification methodology in terms of the tools and scalability. Matches the spike to spike with software simulator for single and multi-chip networks. Okay. So how does this thing works? Talking about the working of it, the chip communicates and process data packets. Those data packets are called spikes. Spikes enters one of the 4096 cores in the chip through input called axons and are processed in the computational elements inside each core called neurons. Each core can be connected to any other core on the chip by two-dimensional mesh networks, and therefore from each neuron on the crossbar to any axon on the chip. Axons can have one of four possible labels. So a spike that enters the crossbar through an axon of type 0 will be handled differently to a spike that enters through an axon of type 1. True North, once loaded with a neural network model, can be used in a real time as a sensory streaming interface engine, performing rapid and accurate classifications while using the minimal energy thresholds. True North's first 1 million neurons consume only 70 megawatt, which is like having a neurosynaptic computer the size of a postage stamp that can run on a smartphone battery for a week or something like that. True North works exactly the same way as the brain. Instead of a small number of big CPUs, it has a huge number of small artificial neurons, and all of them are connected with each other. The picture over here, it defines like the basic layout of the architecture of True North thing. That's it. Thank you. Any questions?
Any questions? I'll use Annie's question, or Ani's question, sorry. What made you choose this topic?
Okay, so I was like exploring the topics and the research field, and last week I was listening to a TED talk related to it, in which some researchers from India, they had, I also added that in the bibliography part, they were researching this, they were doing a research project, and let me tell you that thing. Yeah, and all like they have simulated some of the best possible results from. They were basically comparing these two chips, the Intel one and the IBM one. Both has the BMI interface, and they find out that there were some good results on True North chip. So I thought that it is somewhat related to my topic of computer architecture to talk about.
Okay.
Yeah.
Anything else? Any other questions?
Yeah, I got a question.
Mm-hmm.
What did you find the most interesting about your topic?
Okay, so the interesting thing is like the experiment that I read about it. Uh, Basically, they had a big data set on which they were consuming. They were basically testing the scalability of how to examine big data sets as compared to the brain simulations. And on that experiment, I found something like that. All of the time computer has to process the data, but the human brain doesn't have to. So it has to process the data, but there are some things that are pre-built and premature in the human's brain. So for that, they need something that every other article or every other research project, they were saying that we have to find something related to it that can match, that can give more results and more better results for the neurons matching, and that can only be achieved when they have more synaptical and synomorphic data with them.
Okay, that's cool.
Any other questions?
Going once, going twice. All right, good job.
Thank you very much.
All right, who wants to volunteer next? Or Mr. Gonzalez just starts picking. See, Ani and Maddie, Karan just clapped. I saw his clap. Well, no, he did a digital clap. You said
I
you
still
can't
don't
the
see it.
claps. Camilla just did
Oh,
it?
I see it. Oh, Maddie, it's on the participants. So when you look at everybody's name on the side, that everybody that's here, that's where the clapping icon shows up.
Oh.
I thought it was the videos at the
Thank you,
top.
Camilla. Camilla is clapping so rapidly.
All right, who wants to go next? I think,
Joshua is trying
Can you
to
hear
say
me?
something.
yeah, I hear you now. I was going to say, it looks like
Okay.
Josh is talking to himself.
Okay, I would like to go.
All right, Josh is volunteering.
So hi everyone, today's my topic is that relationship between compiler and computer architecture. So first of all, I would like to explain you what is the compiler. Compiler is a computer program that translates computer code from one programming language to another programming language. And a computer understands instruction into machine code such as zeros and ones. And it is too hard for a computer to write a program into the machine code. So therefore we need a high level of language such as like a Java, C++, or Python. So therefore we need a compiler to translate a program from high language to the lower language. I would like to explain you in a diagram I have, if I can, I don't know, can you see my another photos?
I just see your slides.
Oh, I was thinking to.
Sometimes Zoom will like snap to a window when you share your screen.
Okay.
So it just snaps to an application instead of the whole monitor.
I cannot draw the things anyway. I was thinking like a. Okay, let me explain you that suppose for example one side is we write a bunch of coding language, and then we give coding language to the PC. PC will say, wait 1 minute, I don't know your language, what are you talking about? PC doesn't understand coding language, and it understands only in numerical ways. The programming, and it means coding will translate to the digital ways from zeros and ones, and then it will give to the PC, and then the PC will read. This is the way it works. So that's what. And another thing is, what is the computer architecture? As we know that we have seen a compiler is a program or software which translates one language to another language. When a programming language compiled in it to implemented underlying by the hardware computer architecture. Another way I want to say that compiler is a software related and architecture which is an hardware part. So both are work together, that they have relationship. Without one another, they can't work it. Second thing is that there are two main goals of the compiler. First is correctness. Second is speed of compiled code. As we all know that all valid program must be compiled correctly. That is why they are valid. If it's not compiling correctly, there will be no more valid. A compiler also generates the error message only after scanning the whole program. So normally we can understand that must be correctly, that's why it is compiled. Second thing is that speed of the compiled code. A compiler takes a large amount of time to analyze their entire source code. But also at the same time, overall, it is faster. It is faster. Third thing is that the impact of compiler technology on the architecture decision. In interaction of the compiler and high-level language depends upon what instruction set in structure it works on. Let us look into 3 ways of a high-level language which distribute their data. Number 1 is a stack. A stack is a container of objects that are inserted and removed according to the first in last out principle. In another way, we can say that the procedure of push and pop, you all already studied in maybe Java programming language that push and pop, so I don't explain so much, but I would like to say in this point, stack is used for a local distribution and to keep track of live procedure activation, which is can make understand that they are good or not. Second thing is that global data area. Global data area can be shared by multiple programs. The global data area programs are used for all variable and other structure as arrays. If you do any modification in the data, global data area, that will affect all natural object of global data area. Therefore, before we change the source code of the data area, you have to put all the previous created natural object. This is another is a heap. Third is a heap. Heap is a memory used by programming language to store global variable. By default, all global variable are stored in the heap memory space. It is also support dynamic memory location, and the heap is not managed automatically for you. It is also, heap is not strongly managed by CPU also. It is also, it is more likely free floating region of memories. Factor in architecture that affect compiler optimize. The major factor of affecting the compiler is the machine of which code is to be executed. We are going to see 5 different factors in architecture. We will see one by one what are the 5 factors in architecture. Number 1 is RISC versus CISC. So the CISC stands for Complex Instruction Set Computer. This has CISC has 200 to 250 instruction and has different length of instruction and also addressing mode. RISC stands for Reduced Instruction Set Computer. In that has only 20 to 30 instruction. It has complex length of instruction and also specifying address mode. Any instruction must be passed through that registers. Pipeline. This is the second architecture is a pipeline. Pipeline is a technique where the multiple instructions are overlapped during the execution. Pipeline is also divided into storage. As you see in the picture, is right side is that we can see there are the cars are there, and suppose for example, one car take 24 hours to build the car. So 3 people are building the car and it take 24 hours. That means in 24 hours, one car is ready. Other side, you will see the left side, which is, we can see is the 3 stages, engine, body, and paint. So 3 stages are there. First team is building for the engine, and second team is building for making a body. Another is third, which is painting. So normally how it happened after preparing a engine, after completing the engine part, first team, he will go back to another, make another engine. So there will be overlapping. So my point is that how pipeline area implement in this computer. So therefore 3 stages which instruction pass on computer, which can be say fetch, decode, and execution. So same way, one after one, the car is making, same way fetch and decode and execution will work in pipeline. They are overlapping one another. Number of functional unit. This is the third factor. Some of the architecture has several arithmetic logic unit and also floating point unit. They process certain instructions from program to time. Just like we have seen in a pipeline, these can be independent. This can be approved, stopped, or proper instruction, including different unit PC. Another is cache size and type. Fourth factor in the architecture is the cache size and type. There are 3 different level or categories granted in this case. Example 1, level 1, and level 2, and level 3. Level 1 case is generally built into the process chip. It is also smallest size. Process chip is the smallest size and ranking from 8 KB to 64 KB. However, it is also faster than any other memory for the CPU. Cache, memory, and transfer rates. This is a fifth factor in architecture, which is the cache memory transfer rates. This is the last factor of the memory transfer rate. In this factor, there may be cache collision. It might come in cache collision, or maybe memory can be unusual. In this factor may cause also productivity issue in the same application. So these 5 factors in architecture can affect the compiler effectiveness. I think, thank you so much for listening.
All right, any questions? Nothing? Got nothing? Were you already interested in compilers prior to this, or was this something that you wanted to look more into?
Just I was interested to see how does a compiler and architecture work together, what is the relationship with that, to understand exact what is that. That is the reason why I have did some research about the compiler and architecture, because yeah.
Okay. All right, any other questions? All right, who wants to go next? So we got, who we got comment? We got Seth, we got Maddie, we got Debbie, Ishtiak, and Eric. So you guys can all fight to the death. Who, Ishtiak?
Yes, sir.
All right, you're up.
All of a sudden started raining here.
Yeah, it started raining in Waukesha too.
Can you all hear me?
Yes.
Yep.
Okay. So yeah, I've chosen this topic, Intel Core i7 architecture, the 10th generation Core i7 processor, which is very much interesting, and it is now currently launched, actually, you can say. And also the processor introduction, I have to say, is it is used for multitasking and for highly performance or supercomputers, and also for multi-threading and extreme gaming, and also editing movies. And it has specifications like 8 MB cache memory, which is quite fantastic. And it also have a better cooling system, and it does not heat a lot, rather than the old computers or old generation processors. And also it is very power efficient also. So yeah, the architecture for the Intel Core processors is basically, it has the two portions, in which first one is the core portion that you're seeing in the image, and the second one is the uncore portion, which lies the memory portion, we can say, or the processing portion, the memory processing portion. And the first one is the core portion, in which the all kinds of core processors and all the processors heading into the 8 cores, basically to perform the core processing units. And in the uncore portion, we have like all the basic operations of the processing goes under to the core processors. And in the uncore portion, we have cache memories, and then the powers and the internal memories structures, all of the like a QPI memory, in which it's a quick path interconnection that connects the processes and that connects all the processes to the processing units, and it will transfer to the devices or the signals and get back to what it wants. So this is the main architecture, and we have the socket. Yeah. The other thing is the socket portion, in which the architecture uses is LGA 1633 architecture. 1366 architecture, and it is incompatible to the previous core generations. So it is a new socket architecture also, and it is very much stable for the power supply. That's why this processor is very much power efficient, and also it provides the high pin density, so as to give more tasking abilities via ports or external units. And we have lastly the chipset, and we all know that chipset is a group of integrated circuits, and it has it consists of the two parts. One is the northbound bridge, and the other one is the southbound bridge. And it's actually, the chipset is used for the communication between the processor and the external devices. And for example, like for the sound units, and for example, the network cable, all the ports that we'll be using are going through the chipset manner. And it's actually basically the communication between the processor and the external devices. So for like, there are two parts in the chipset. There are northbound and the southbound. For northbound is used for the high-speed devices, as the chipset for the southbound uses for the low speed devices. For the high-speed devices, northbound architecture uses, for example, all the kinds of memory. For example, the hard disk memory, or the main memory, or the RAM unit, and also for the graphics controlling all kinds of high-speed devices that undergoes to northbound bridge, and the southbound bridge extensively goes to the low speed devices such as the Ethernet and USB and audio video devices, etc. And also the power, and it comes under here, and we can think and we can have an idea where the power will be low, and all the kinds of BIOS settings that comes under these settings goes to the power architecture. So the key features of the Intel Core processors is the integrated memory controller, in which we are using, I came to know that there are Van Neumann architecture and Nehalem architecture, and many kinds of different architecture that Intel uses. But for the Intel Core i10 generation, it uses Nehalem architecture, which we can see in here in the diagram. And integrated memory controller is example of a memory within the chip, and you can see in the image that the processor, and after that it has returned the memory controller, and the outside portion it connects to the memory. It actually what it does is the memory is an example. I've given the example as an Intel Octane memory. Is actually uses all of the daily activities and store it in the memory controller as a type of playlist that you will be using, and you will be like get used to when you start any application. We have like for example, the song application in our phones and the Microsoft application. So for which song do we left on that side, we will come to know that, okay, we have to, I was here and I have to continue from there. So this kind of all information and all easiness or contain the logics necessary to read and write to the RAM. It's used by the integrated memory controller. So it acts as an AI performance and AI efficient processor. So it is a key feature of the integrated processor iCore i10. And the another one is the Intel QPI that I've said you is an Intel Quickpath interconnect for launching the apps and for giving the speed you want for booting the system. So it's just, you can see in the diagram that it connects the memory to the input-output controller, and it acts an interface between the processor and the rest of the computer devices. And it is independent because it does not hold any connection with the other parts of the computer. So independent of the other modules, we can say, for example, we have seen in the architecture, the core module and the power module and the cache module. So this type of things, this type of the modules which are not related to the Intel Quickpath interconnect architecture. So here actually the data transfer per second. So instead of frequency, instead of hertz, the frequency matters is the data per second. So basically a BCLK, which is a term which is used for the instructions here as per clock. So base clock is in the times per second. And the another key features was like I've came to know about, and we also know that all the processors, previous generation processors are 14 nanometer processors or more than that, but now it has been morely reduced down to the 10 nanometer size, and it's a good design. And I've talked about the LGA 1366 design. So it has been now down to more nano size, it is 10 nanometer, and also it uses hyper-threading technology as the previous one, but it has been increased because of the Intel Optane memory that uses and combines them both to make more efficient, more power efficient, more also make it fast as a fast processor. And we also know that in previous generation processors as the turbo boost mode, in which we have all kinds of turbo boost technology, and in here it has the instruction, it has turbo overclock as the basic is 1.6, but it can boost its technology, its turbo boost mode up to 4.5 gigahertz, which is a huge amount of clock cycles per second. And if we want more amount of heavy gaming or extreme gaming and any kind of animation systems or the applications we have to use, and then it automatically turns on the turbo boost mode, and it also gives the amount of performance that you want. And the interesting one is the SSC 4.1 and 4.2 instruction set, and the blade has been talked about somewhat of it. So actually the streaming amount of single instruction and multiple data instruction set is like for the 32-bit architecture, but we know that this is a 64-bit architecture processor and the motherboard. So it uses So it uses 4.2 and 4.1 and also 4.3 in some sources. I have came to know about reading some of the articles that it uses instruction set for mainly for doing a number system to calculating the zeros and ones in a very quick manner. And the last one, I came to know about the futures of the Intel i7 core i10 generation is the overclocking speed that has been I've used here as a program as a diagram for determining these into stats. And we know that in the previous generations, and though the modular design was more than 40 nanometers, and it has been gone to 10 nanometer now, but you can see there is a overclocking speed of 4.6 and 3.9 here. And though it has been like uses a less amount of nanometer, but it has turbo boost and overclocking speed more than the previous generations. And this is the way. And also the stats that have been the benchmark, we can say, have been taken from an article of the PCWorld.com, in which it gives the two types of processors, basically the Ice Lake processor of the I'm talking about the Core i7 10th generation. It has two types, the Ice Lake processor and the Comet Lake processor, and the Whiskey Lake processor and the Sky Lake processor. So these all kinds of processors with hyper-threading technology has produced more and more efficient way and more high performance in terms of, and you can see the Dell XPS 13 here right at the bottom. It uses the Core i7 8th generation processor with the Whiskey Lake, and it produces more amount of amount of hyper-threading technology when it can, and you can see the SDS Core i7 10th generation processor, which is a huge amount of more 758 threading performance now. So my conclusion about the Core i7 architecture, as we know that Intel is a technology which where everything is going to be becoming very nano and becoming more obvious with the performance and more obvious with the memory. All the issues will be solved in upcoming years, and it will be like we don't have to worry about the data. I mean, we don't have to worry about the amount of performance or amount of speed we want. So thank you, sir.
All right, any questions?
Just a little question, since you also mentioned about SSE 4.1, SSE 4.2. Do you happen to know how many IMD inside Core 7 architecture?
Okay, so I don't know about how many it consists of, but I came to know the architecture uses the instruction set cycle, and which are the versions that I was taking into account was like key specs or the most important things that Dr. Lippmann said to deep dive into the topic. So I've just taken the amount of versions that it uses, like 4.1, 4.2, and 4.3, which is obviously more advanced when we are dealing with the SRAMs and we are now dealing with the DRAMs.
Mm-hmm. Okay. Yeah. I also didn't really find any like clarification of how exactly it is, but since SSE 4.1 and 4.2 should be compatible with the original ones, so at least they should have at least say 16 register in each core. So that is, I say at least it must have 16, but but I read something says it have 128 actually.
Yeah, maybe like it's a iCore 10th generation, so I'm expecting to be more than the previous versions, and we expect everything like to be more in terms of all the things rather than only the instruction set cycles or the anything about that relates to the architecture set.
Yeah, that's it for my comment.
Okay. Thank you.
All right, who wants to go next?
I do.
All right.
All right. Is that sharing?
Yep.
Good topic.
Yeah, I really liked the Intel architecture. All right, whenever you're ready.
I'll start my watch. Okay. So I did my presentation or my research on smartwatch architecture. And the reason I did this is because it's something that I use daily as my smartwatch, and I've had it for a really long time. If my smartwatch that I have right now dies, I know I will get a new one just because I use it all the time. And so it piqued my interest, and I didn't know a lot about it, so that's why I studied it a little bit. So just a little bit of introduction that smartwatches have been around for probably longer than you know, but the first, a little bit of a timeline here, is the first Garmin Forerunner, which was my first smartwatch, was first created in 2003, and the Nike Plus Fuel Band was in 2012, and then probably the most familiar that people know is the Apple Watch, which was in 2015. And so the market for wearable technology is booming. And as we go forward, we know that the medical industry can also have reasons that they would like this technology to increase in the different sensors and capabilities that they have. But ultimately, selecting the right microcontroller for these devices is important. And so I will be talking a little bit about the architecture within these and how these watches have to be able to handle many different functions. So if you break down different categories of smartwatches, it can be into these 4 categories. The first one is sports, which is capabilities that will track or that have a pedometer, calorie consumption, weather forecast, compass, and GPS. Second is health tracking. Third is security. Fourth is alerts. I probably use the alerts just as often as much as I use it as a watch, just because I like to be able to read my text messages and view notifications and see reminders and things like that. I haven't used it on my watch, but security is another one where you can, if you fall or something on a run, or if you're in an emergency, you can call someone or alert someone with only your watch without having your phone. And that's due to the GPS tracking that's within these devices. And then, of course, health tracking is another big one where there's heart rate monitoring, which I will talk about at the end, body temperature, and sleep monitoring, which I will also talk about at the end. So some requirements for smartwatch, obviously, aesthetics, we want it to look nice, but also size is a big requirement in how big we can have our processor and all the sensors within it. Water tolerance, power consumption, wireless communication. I said this before, but the correct app processor or microcontroller and operating system. touch sensing, because a lot of these watches have touch screens, and long battery life is very similar to power consumption. So all of this has to go on in just something that we carry around in a watch. So that all can be accomplished with the ARM architecture. I read multiple articles that said that the ARM architecture has the best performance and energy efficiency for this job. One quote that was in an article that I read said that the ARM Cortex-M-based processors are able to sense, use, interpret, and securely share data from their devices. And the security is a big thing because it is kind of my theme, I guess, of the semester so far has been Internet of Things devices, and this is obviously one of them. And so being able to have these watches not only use their sensors to gather all of this information, but also take care of that data and transmit it securely. And that's what the ARM Trust Zone technology is for. So within these watches, or these smartwatches, are basically just a bunch of sensors. And so we can break those up into these categories here. We have motion sensors, biosensors, environmental sensors. And so all of these have to be capabilities of our watches, or in some of them, not every watch does everything. And I mean, you can read it here, but there's things like temperature tracking, humidity, microphones in watches, and each of these sensors collects data on the user and his or her surroundings that are then transferred to the CPU. So this was a picture that I found that I thought was very helpful for seeing the different aspects of what could be inside of these smartwatches. So not every, I guess, part of the smartwatch is outlined here, but I'm not sure if you can see my mouse, but I'm gonna kind of point with it. So here we have the ROM in yellow, and then if you keep following the colors, we have RAM, we have the CPU, the microphone here, and then the pulse oximeter, I think that's how you say that. And then right here, the gyroscope, I think is how you say it, I had to look it up. And so now I will tell you about some of the different companies that where you can buy these things. I kind of ignored this column here, but just going across here for some of these different companies, for like Bluetooth and Wi-Fi, which our smartwatches connect with, we have Broadcom. Some other ones I think are on the next slide here. UV sensors here, Silicon Labs. Texas Instruments comes up a lot. Non-contact temperature sensor. And let's see, UV sensor, oh, I said that one. So all of these are the different sensors that, or different parts of the watch that we use and need to make the watch work. And so, my next topic that I kind of went into, I read one article on this, and I think a lot of other people mentioned this, but I had a hard time finding articles that at least I don't know if you can hear the dogs, on the library website. I had a hard time finding articles. So, but I did want to touch on how our smartwatches track heart rate, and heart rate is calculated through the LED lights in the watch itself. So if you have a smartwatch that you turn on the heart rate capabilities, you can often see those lights on the back that goes up against your skin. And the LED lights in the watch itself, and what they do is they look at the capillary veins in your wrist and measure how fast your blood is pumping. And then a question that often comes up is how accurate this is. And it was really fascinating to hear this because I knew it probably wasn't that accurate, but I didn't understand why. And one of the things that I learned was that at our extremities, which means like our hands and feet, our blood pressure is slower than it is closer to our heart. And so so even when you are exercising or, I don't know, anything, talking to friends, speaking, anything, it is important to make sure that you sit still and don't talk and you're quiet and let it sit for just like a minute and then be able to, and then you can look to see, and even then it's still not accurate because a statistic found that it is on average about, I think the number was 5 BPM, beats per minute slower, and it can be up to as much as 50 beats per minute off, which is a lot. And so it's definitely take it with a grain of salt. And then, oh, I guess I could have shown this. So there's the lights, and you can see the different sensors there. And then the last thing is how do smartwatches track sleep, and the sleep capabilities happen through what's called an actigraph, which measures your body's movement when you're sleeping. And some smartwatches also have microphones, and it can listen to if you're snoring or moving or talking in your sleep, which have all been linked to sleep apnea, which is another reason why some people like this data, because they can use it for health reasons. And then, like I said in the last slide, it can track heart rate, and when you're sleeping, your heart rate is obviously or usually not as fast as it is when you're awake. So I think that's all I have time for. Make sure you wash your hands at the end. Any questions?
All right, so Ani gives me a hippo destroying a crocodile, and I get hand washing.
Yes, yes, Maddie.
Please. I don't want to get sick.
Okay, I have a few things I want to say.
Okay.
Okay.
Brace yourself.
Brace yourself. Ani is gonna speak. So I actually wear a heart rate monitor when I work out, and I also have a smartwatch. And there was one time when I first got the watch and the belt that I wanted to wear both of them during a workout to see if the stats were different. And it was different. The heart rate monitor was a lot more accurate. There's a few times where my watch thought I was dead when I wasn't. Yes. So yeah, just kind of like going off of what you said about the reason why it's not as accurate is because it's on your wrist. It's not as close to your heart as if like you're wearing a heart rate monitor, right? It's going to be more accurate because it's closer to your heart. And then also kind of interesting, when I first started wearing my smartwatch, and it also tracked my sleep too, right? I could actually, and I don't know, I could be crazy. I'm just curious if you guys, those of you that have a smartwatch, I could feel that green light on my skin. I don't know if you guys have ever like noticed that or anything in that. Like I couldn't sleep the first few nights that I had my watch on.
I couldn't sleep with I couldn't feel the light, but every time I think feeling the light.
I don't know what I was feeling, but I could feel something.
Sorry, we are not white.
The light wake me up, so I couldn't.
Yes, that too. I need to like send them an email and say like, this is ridiculous.
So the green light actually it checks the heart rate when you are not moving. It sets from default that it will check in R rapidly, like it will check the blood pressure pumping. Then there is a feature there, if you don't move for 15 minutes, the app can call SOS and something. Yeah, I also was worried that why is the green light is always up here.
Mm-hmm.
Yep.
Okay. So that's interesting, that Maddie. I gotta do some research on like what exactly when you're like getting shot with that green light, like what also is happening, right? So yeah,
Yeah,
I
it
thought
was really interesting because I think they do some weird magic, probably some calculations, but it's weird that it can just like read our veins through the light.
Yeah.
Also, you're supposed to wear it really tight, and I don't wear it tight, so that's why I don't pay attention to it
I
very
mean, how
often.
accurate do you want your data? Like,
I mainly only use it for like recovery in my workout. Like you're supposed to like between reps or whatever get your heart rate down to a certain level, and that's what I'll use it for.
Cool.
Speaking of the smartwatch, I recently read something say, I think the Apple says iWatch will adding the measuring for the oxygen inside the blood. That is really curious how it made it.
Was that a question?
No, not a question, just a
Oh,
comment.
yeah.
Interesting.
It was really interesting to me because I never really thought about like just how many sensors are in these smartwatches. I'm not sure if mine has a microphone because mine isn't an Apple Watch, and I think the Apple Watches do because you can call people on it. I can't do that on mine.
Yeah, I don't have one either.
Actually, I can call, but I can't talk to it, I don't think. But that seems to make sense though. Like, I don't know, we rely on these things to do so much for us, but they're tiny. Okay, that is all. Thank you for listening. Wash your hands.
All right, who wants
We
to
work
go
on
next?
computers. They're germ infested.
So?
I can go next.
I'm just saying that Ani had a hippo eating a crocodile.
I've got a palm tree.
I never
blowing.
said that mine was better.
Well, that would be a lie if you did.
I would lie?
I like
Or it would be a lie.
Maddie's.
It would be a lie.
It's logical. Mine had no sense.
I have no opinion. I'll be sure to add something next week. Just for you.
All right. Before I get into my presentation, don't start the clock yet. I don't think I've ever really introduced myself to everyone. So my name is Seth. It's very nice to be your fellow classmate in this class and busting our brains on research topics. A little bit about myself. I work here at Concordia. I work in the IT department, so I'm a database administrator here. And I think you're looking at my database right now. It probably looks like it's got a smartwatch on monitoring things. So this tells me what it's up to. I spend a lot of my time writing SQL queries, which look like this. Well, actually, this is creating a table. I work a lot in Linux. So this is what, if you work in Linux, it's kind of like looking at the mainframe. And then last, on a personal note, I am married and I have 3 kids. There's my lovely wife. There's my lovely 3 kids. They're grimacing because they're really cold. So, okay, now I'll start the clock.
They're so cute.
I think
oh
they're
my
cute.
gosh, your kids are so cute.
So yeah, they try to get away with a lot. So anyways, we don't have any pets because the kids are enough work. So pets would add overcomplication to that. Let me share out my presentation.
Is that Door County?
That is Door County.
That's awesome.
So if you're staring at a computer all day like we are, you might as well have a background that like inspires you to go outside.
Oh yeah.
So okay.
I definitely do the same.
So quantum computing, the art of getting the dot in the right spot. I don't know if my tagline's correct. That happens to be my understanding of what they call the double slit experiment, which maybe we'll talk about. Let me grab my notes here and I will start talking about quantum computing. Okay, one moment, please. I gotta minimize a few things. Okay. So here's just a quick picture of an IBM supercomputer, IBM again. And actually, there is IBM's quantum computer. That's one of their superconducting quantum computers. So the best way to, for me anyways, I will share what worked for me and hopefully it works for you. The best way to understand what a quantum computer is to look at a, quote, classical computer. A classical computer is actually the IBM supercomputer. It's just a computer that processes information in bits and zeros and ones. We've already had a few presentations that have referenced that. So a classical computer works on information where the unit of information is called a bit, which is a 0 or a 1. A quantum computer, by contrast, actually uses a similar but very different unit of information called a qubit, which is short for a quantum bit. A bit in a classical computer can be a 1 or a 0. What makes a qubit different in the quantum computer is that it can be 1, 0, or a combination of 0 and 1 at the same time. And when the qubit is in a state called superposition, it's 0 and 1 at the same time. And that's half of the secret sauce that gives a quantum computer its computing power. So a classical computer with n bits can be in one of 2 to the n possible states at a given moment. So that means all the information that we have, say in the processor and the memory, that's a big long binary string. It's going to be one of the 2 to the n permutations that are possible when we read the state. A quantum computer can be in all the 2 to the n states simultaneously. So what a quantum computer do, because it can be in superposition where it's 0 and 1 at the same time, where a classical computer is going to go through something one by one, each possible binary string one by one, a quantum computer can have all the binary strings up and going at the same time. A classical computer with a 32-bit register in its CPU could have, let's see, I have got 4 billion, about 4.3 billion possible states that it's in. Now, a classical computer will be in one of 4.3 billion states in that 32-bit register. A quantum computer with a 32-bit register would be in all 4.3 billion states simultaneously. So a classical computer is going to pick one state and it will be in that state. A quantum computer will be able to be in all possible states. What this means is that when quantum computers are finally realized, when they reach quote unquote quantum supremacy, they will be extremely useful for doing calculations that would take a classical computer a long time. Quantum computers, it's not a matter of them being able to do computation that a classical computer can't do. It's just they can do it much more quickly because they can put everything into a superposition state and an entangled state where they can get to the right answer more quickly. Okay, a bit more about qubits. This all I've got. I wish I'd now done a hippo or an alligator, but all I had was the matrix. Quantum computers take advantage of quantum mechanics. In particular, they take advantage of something called particle wave duality. We won't talk about that because that would violate the rules of the presentation, which is quantum for lay people. But basically, in quantum mechanics, things behave as they shouldn't. So it reminded me of the Matrix where Morpheus and Neo are fighting, and Morpheus is trying to tell Neo how he can fight better in the Matrix. And I think he's telling Neo basically be a quantum computer. Don't follow the laws of classical physics. So as a quantum computer has qubits, in our classical computer, we have bits, which are transistors somewhere on the chip. The transistors flick either on or off, and we're able to make an integrated circuit that way. A quantum computer doesn't have anything to do with that. It actually makes qubits, and it manipulates qubits at the quantum level using such things as microwaves or laser beams. Qubits can become entangled with one another, and what that means is the behavior of one qubit instantaneously affects the behavior of another qubit. So unlike an integrated circuit where everything is going to be linear, if I flip something on, if I put a bit through a NOT gate, it's going to downstream affect the AND gate. An entangled qubit, when I flip a 0 or a 1, or if I do something to its superposition where it's in that both AND state at the same time, it's immediately going to affect all the qubits that it's entangled with. Qubits lose their ability to simulate all possible states when they're measured. This is one of the mysteries of quantum mechanics. When we measure a qubit, it will collapse to a 0 or a 1. So we can't actually see the qubit simulating all possible states. All we can do is take a measurement and we'll get one of the possible states when we measure it. The last thing to know about quantum computing, what makes quantum computing really hard and why we don't have quantum supremacy is something that they call decoherence. Qubits are by nature extremely fragile. The qubits will be in a coherent state where they're in their superposition for literally microseconds, maybe like 1/100th of a second, and then they decohere. So it's really important in quantum computers, if they're doing a calculation, that they're able to read the quantum state quickly and that the quantum state is not full of errors. And because of outside environment, there can be a lot of noise that can affect how the qubits behave. And one of the most important things they do is try to isolate the qubits so that they are not affected by any environmental factor. It's another reason why we don't have quantum computers. For example, IBM, this computer right here, it takes them days, literally days, to get it cold enough to where the qubits are isolated from the outside environment so it can do quantum computation. So it's not quite like the supercomputer over there. I imagine the startup procedures for that thing are amazing, but I doubt it takes days. Literally for this computer, the startup procedure can take a couple days because they have to get it cold enough. All right, we will do a quick look at a quantum calculation, look at the secret sauce at what makes these things so amazing at a very small scale. Oh, by the way, going back to decoherence, one of the articles that I read about this says that as quantum computers are doing calculations, by the way, I'm not this smart, this is just what a quantum calculation looks like. As it's doing a quantum calculation and figuring out the superposition of the qubits, the information on the qubits rises up like a ring from someone smoking. So if they were smoking and blowing smoke rings, the information is there as long as the ring is intact, but as the ring goes up, it dissipates. That's basically what decoherence is to a quantum computer, and it's one of the biggest challenges that they're having with them right now is how do we keep things reliable enough to actually get a long use out of this. So, as I said before, qubits can be in a superposition. That means they're going to be 1 and 0. They're going to be in some state in between 1 and 0. And we don't know how close to 1 and how close to 0 the qubit's going to be when we measure it. So we're going to take a 2-qubit quantumation, or qubit computation, excuse me, right here. And there's going to be 4 basis states or basic states that the qubit can be in when we start the computation. This notation right here is called bracket notation, and it's how they represent a qubit. And I think I skipped over it. Over here on the right side of the screen, when a qubit is in the 0 bracket notation, it's 0, 1, and when it's a 1, it's a 1, 0, representing the fact that it's either closer to 0 or closer to 1. But, you know, it's somewhere in between them. It's not. Anyways, the good news is I read Albert Einstein was even confused by this. So if you're confused by this, so is Einstein. So here's our 2-qubit computation. And what we're going to look at here is what they call the oracle function. This is an application of quantum computing that in itself isn't useful, but is a proof case of how a quantum computer is better than a classical and more efficient than a classical computer at computing certain things. So the basic idea would be that if we get a 0 or a 1 and we pass it into a function, so we take the first qubit and we pass it in, we either get a 1 or a 0 out of it. And what we're looking for are constant or balanced functions. If no matter what the qubit is, we pass it in and it comes out a 0, then we have a constant function. If it switches when we pass in a 0 and a 1 or a 1 and 0, then it's a balanced function. To figure this out in a classical computer with a 4-bit register would take, let's see, 1, 2, 3, about 4 steps. A quantum computer working on a quantum circuit can figure this thing out in 1 step. And the way it figures it out is right here on the bottom. This is a qubit in a superposition. And all this fancy math means is that there is a 25% probability that when the quantum computer measures the qubit, that it will get out one of these answers. So there's a 25% chance, just ignore the square root, just think of it at 1 over 4. There's a 25% chance it would get 0, 0 out, 1, 0, 0, 1, 1, 1. And of course, this is 0, 1, 2, and 3. These are binary numbers. So we could get 0 through 3 out of this. And there's a 25% chance. By itself, this measurement from quantum computing is useless. We actually would have to do the same as a classical computer. We would have to measure it 4 times and say, oh, okay, based on these 4 measurements, I now know whether this is constant or balanced. But using quantum logic gates, we can actually affect these numbers. By the way, these numbers are, again, probabilities. The probability is what we're going to get when we measure the qubit. Quantum logic gates can actually affect the probability of what will be measured. So say we have, let me find one of these fancy names of quantum gate. One second in my notes. If we have the unitary gate, or there is a gate that starts with H. Hang on a second. Oh, never mind, I lost it. There's a bunch of different gates that can be used in a quantum circuit. They're like an AND gate, they're like a NOT gate, they're like an OR gate, but they're a lot more powerful, which is why a quantum circuit can do this in one time. What we can do while the qubit is in its, oops, come back. There's another Door County shot for you, Ani. All right. While the qubit is in its superimposed state, it's actually behaving like a wave. And these probabilities are actually something that they call amplitudes. It's possible for us to feed a qubit through quantum gates in a quantum circuit and mess around with the amplitudes of what we measure. So you see here that we've put it through a superposition, and we've made it a lot more probable that when we measure it, we're going to get 0 out, as opposed to 1 or 3. There's a 0% chance of getting 2. This is basically the goal of quantum computing, that when we pass our superpositions through what they call a black box or an oracle, where something happens to the superposition that we can't see, we can actually affect the amplitude of the decoherent, or excuse me, the superimposed state that will give us the answer that we need to have. So you start out like this, where everything is an equal probability being measured. And by the way, that's not how it would work in a real quantum computer. The probabilities are going to be affected by all kinds of things. But through the quantum gates, you can actually figure out and get it close to, I think I read that they like it at 99.99% certain. They can get a quantum gate for certain computations to be that accurate. And when it's that accurate, you feel pretty good that the superposition that you measure from the possible states that the qubit could be in is the right answer to your equation. I wish this was longer, but honestly, when you read technical articles for quantum computing, it takes your head a while to wrap itself around the linear algebra that's involved with here. So that's all I have. This is the basic proof case of how a quantum computer works more efficiently than a classical computer. This is a very simple illustration of what they call the Deutsch oracle. This kind of math has been used to prove things like Shor's algorithm that shows that a quantum computer can factor prime numbers in polynomial time, which is something that a classical computer cannot do. One of the articles that I read was on the state of computing at the end of, or in the 21st century. And they said one of the biggest challenges that we're going to have as quantum computers mature, and they're not mature yet, but they're getting there closer year by year. One of the biggest challenges that we're going to have is we're going to have a quantum computer that can implement Shor's algorithm. And when that happens, all information on the internet using SSL will be able to be decrypted. So one of the active areas of computer research right now is what they call post-quantum cryptography, which is the search to find a way to encode our data that can survive quantum calculations. Okay, that is all I have. Questions?
Any questions?
I have a few questions.
Yeah.
First of all, is as it mentioned, there is say 99% blah blah chance to be accurate. So how they take the possibilities outside? Say when you are doing something, how it can guarantee it works?
They have very rigorous math, and honestly, I don't understand combinational math or TensorFlow well enough to tell you how, but as you read the mathematics, they can prove to you, if you can follow the math, this is how it works.
So it will work, even though it is based on possibilities.
Correct, it will work. Actually, the problem isn't the theory. The problem is actually getting a quantum computer that can stay coherent enough and to do these calculations. Apparently right now they have to do a lot of error checking. So they distinguish two things with qubits. They distinguish physical qubits and logical qubits. Logical qubits are what make up the circuits in a quantum computer. But in order to get one, say, logical qubit, they actually need to make like 100 physical qubits with lasers. And the only job of those qubits is actually to affect those probabilities to eliminate the error so that the probability amplitudes are really high. So they need an incredibly high number of what they call error checking qubits to get one logical qubit. That's actually one of the big hurdles that they're trying to overcome right now, is as they scale out and add in more logical qubits, they need, for lack of a scientific term, they need a whack load of error checking qubits to make the quantum computer work. And of course, given the fact that the more qubits you have, the more prone this thing is to decohere, then of course that's a further challenge for them.
Another question is how actual, so will our currently program be migrated to quantum computer, or do we need to, so how easy it will be migration for the code?
I don't know. One of the things that they say is that the kinds of programs that we will do on quantum computing don't necessarily have to do everything a classical computer does on a quantum computer. There are some programs where it doesn't actually make sense. It's like a classical computer and a quantum computer are going to do them just as efficiently. Like my example with a 2-bit register, that's nonsense. Our classical computers with their billions upon billions of bits, they can do that no problem. So you actually need a quantum computer with 2 to the n qubits where it has more superposition states than the most powerful supercomputer has bits, if that makes sense. That's the kind of computation that makes sense to do on a quantum computer.
Thank you.
Yeah.
Yeah, also, I too want to ask a question, Seth, that what is the application, and I want to know the applications of the quantum computing.
Sure. Let's see if I can remember. Can't remember my password. I think I have it right. Oh, here it is. Quantum computing, there's 2 big applications that I can think of. One is molecular modeling. So modeling molecules. Our best supercomputers can't actually model molecules very efficiently. And the reason is because when you take a bunch of different atoms and you put them together, you have to account for an extremely exponential amount of electron states. That is, would it be NP incomplete? I can't remember what the polynomial time is in information theory, but it was going to take a ridiculous amount of time for it to do it. Whereas a quantum computer, they're very confident that we're going to be able to do efficient molecular modeling. We might even discover new materials as a result of quantum computers doing molecular modeling. The one I mentioned before is cryptography. You know, it could be that China, the US, more powerful governments have quantum computers that they're not talking about, because we already have algorithms out there that would show us how to break the encryption schemes that we use. By the way, if you want to know what a quantum computer is good for, the United States has a bureau called NIST, the National Institutes of Standards. If you go look at the NIST algorithm zoo, these are all the quantum algorithms that are out there. Not all of them can be put into practice right now, but this is at a very high level, the kinds of algorithms that can be done that would have real world applications.
Yeah, okay, thank you. And also I have to add a comment that I was just also expecting to give presentation on the quantum computing, but I read some of the research papers and the articles, and I have like the amount of max that you are talking about is way beyond to understand, sir. Yeah,
I tried.
Beyond.
So
it also uses many kinds of formulations and a lot of max and quantum physics also, and we cannot understand, and we cannot correlate with this.
I've been telling it to my wife to make her think that I'm smart. She doesn't actually know that I don't know what I'm talking about, but anyways.
Yeah, I appreciate you because you have done a good job
Thank
on
you.
giving presentation for the quantum computing. Thank you.
You're very welcome. Something you guys can sign up for with your GitHub accounts is the Quantum Computing IBM. They've got this thing called the Field Guide to Quantum Computing, and it's an introduction to it. And even this I found hard, but at least they tell you before you start, learn how to code Python, and then take this, think Python, learn Python, take this linear algebra course, then take this quantum mechanics course. Linear algebra, which is intimidating looking, is apparently not too hard for those of us who are university educated.
Yeah.
But anyways, that's what you need. You literally need that to do this. And what I've read is because many computer scientists think that quantum computing is around the corner, it is wise for us to learn at least something about this. I don't know, Mike, what do you think? You're more able to understand this than I am. How close are we, in your opinion?
Well, you mean for like regular use of quantum computing?
Correct.
I would say closer than we probably think we should be, given that the people who are playing in this pool, I would say namely Google, is probably going to find some, let's call it cool uses of quantum computing sooner rather than later. They have the funds, they have the technology, and kind of it's almost like a race for the moon, it seems like right now. I think the biggest question mark moving forward is what kind of problems do we really want to apply quantum computing to, or what makes it show off, as opposed to, I could see them trying to solve traditional problems with a quantum computer just to say we can do it with a quantum computer.
Right, right. And
so
that's kind of what they got in trouble with
in the next
last
5
year.
years.
Yeah, last year Google said, hey, we've got quantum supremacy. IBM pushed very hard back against them, said, no, you don't. There is a very intellectual guy in Israel. His name is Gil Colley. He's a professor of mathematics. He's a quantum troll. He doesn't think that we'll ever be able to do quantum computing because of the decoherence issues. It's actually really interesting when you watch academics troll each other, because it's very smart. You know they're mad at each other and are making fun of each other, but they're doing it at a high level that only they can understand. I'm putting some, oops, I should have put them in a little bit better. This PBS series is actually very good at explaining quantum math for a very lay level. There's a professor of mathematics, Cornell maybe, she's at, and she'll walk you through some quantum computing stuff. I will also put this one in. This is the IBM. This is just for the curious. And I have three more. All this stuff goes back to something called particle wave theory. So this next one is particle wave theory from PBS again. And kind of like the US's version of the BBC, that's what PBS is. And then there's a cartoon, Captain Quantum, but it's actually pretty easy to understand. You don't need linear algebra. There, I gave away my sources. Captain Quantum, the cartoon. All right.
All right, so who wants to go next? Who do we got left?
I'll go, sir. Hello?
Yep, go ahead.
So my topic is NVIDIA GeForce RTX and GTX as well. So as we all know that NVIDIA is, can you all hear me?
Yes, I'm thumbs upping you because I like video game cards.
Yes, yes.
Okay. So as we all know that NVIDIA is a manufacturer of graphic cards, and it supports most of the desktop computers as a GPU manufacturer, and as well as for the laptops as well. And apart from that, it supports in scientific inventions, scientific innovations as well, like in deep learning and AI as well. Recently, it got, recently it got into laptop and portable computers to increase their market in the creative field as well. Like it got tied with the Adobe Creative Cloud so that the Adobe applications can use the GPU power to boost their performance as. So not many computers are, not many laptops are not supporting these kind of features. Like Adobe has got tied with the NVIDIA for only few products. Like Intel has designed a creative computer, and HP as well. They have few creative computers which were released in this 2019 and 2020 starting January. So they have released, but they are not officially announced now. And So next, when we speak about NVIDIA's history, it's actually found in 1993 by 3 Americans, computer scientists. So Jensen Huang and Curtis and Christopher, those 3 guys who put their efforts in inventing this NVIDIA GPU. So GPU, in the sense, it's GPU is the chip which we call, and the chip which we place on the silicon board, it's completely called as graphic card. And its first GPU, which NVIDIA built, is a GeForce 256 GPU, and it's released in 1999. So after that, it took over the gaming industry and 3D modeling industry into a next level with this GPU. So we are all talking like GPU. So what is GPU? Let me clarify that. So CPUs are capable of performing a wide range of tasks, but it goes in a single way. But it can't process everything in a single time. But whereas GPU, what it does is it does parallelly. But they are limited to only few tasks like gaming, 3D modeling, and multimedia. So the only advancement in GPU architecture is it boosts the performance speed by taking multiple instructions, and the GPU is built on a microarchitecture, which is different from an architecture, because microarchitecture is a part of an architecture, but it's not a complete architecture. In architecture, we have instruction set, register set, and exception model and memory model. But in microarchitecture, what it does is it tells how the processor to work. And the cycles, the pipeline layer, these are all part of the microarchitecture, and the cycles are measured in T-flops or flops per second or per minute. It's calculated in that way. So these are the architectures which were invented by NVIDIA. So the first architecture, one of the first architecture is Fermi architecture, and then the list goes on. The latest 2 architectures which took the NVIDIA's market into another level is Pascal architecture and Turing architecture. Before that Pascal architecture, we have a Maxwell architecture, and Maxwell architecture is a successor of Kepler architecture. So I'm just gonna give a brief about Pascal architecture and Turing architecture. So here architecture means it's a microarchitecture, not the architecture which we generally use in the computer architecture. So 2 of the main prominent products of NVIDIA GPUs are NVIDIA GeForce GTX and NVIDIA GeForce RTX. GeForce has been since 2016, and GTX has been almost since 2016. No, before that, but the 10th series GTX series, it's been from 2016. And in GeForce RTX has been launched in 2019 mid, I guess. It's still under, they are still trying to get the boost which they didn't get after the launch. So what is Pascal architecture? So as I said before, Kepler architecture is Kepler architecture successor is a Maxwell architecture. In Maxwell architecture, we didn't have any much improvement when we compare it with the Kepler architecture, except for the energy efficiency. Because in Kepler architecture, it used to use 28 nanometers processor, and whereas in Maxwell, they still use 28 nanometer processor. So it didn't give any competition with the with its computer AMD, which was using 14 nanometer processor at the time in 2016. So in order to compete with the AMD processor, they have introduced this Pascal architecture in 2016 mid, I guess. So this Pascal architecture is completely different from the Kepler architecture. It has three new features in it. These are mixed precision, NVLink, and 3D memory. So mixed precision is nothing but it enables GPU to compute 16-bit floating point accuracy as accurate and fast as 32-bit floating point. And NVLink is nothing but it's a bridge between two GPUs. So previously, instead of NVLink, it's used to use SLI, which is which is having many drawbacks in it, because in SLI, what it does is if there are two GPUs, one GPU acts as a master GPU, master graphic card, and another graphic card acts as a slave, which means if there is if we are designing a 3D model, and what this master graphic card does is it distributes the workload between the other GPUs which we have in the computer. It may be two or three. The main master card just distributes the workload accordingly to other GPUs, and it waits until they are processed and returned back to the master card. So what happens here is, even though we have powerful GPUs in our computer, there's a time delay in it, because the other GPU should render it and then give back the signals to the master GPU. And all this happens on 2 Gbps bandwidth. But with NVLink, what happens is, if there are two GPUs, they are connected bidirectionally. There is no master, there is no slave. They are equally important. So if the workload is distributed evenly, and the communication is also done simultaneously, that too on 25 Gbps bandwidth. So the communication between GPUs is much faster than the SLI which they previously used in Maxwell architecture. And 3D memory is nothing but, previously you can see the hardware board here. Previously the memory chip which was there on this which is on this hardware board, it's on the bottom side of the hardware board. Previously in Maxwell architecture, that is 10 series graphic cards. Not 10 series, 100 series, like NVIDIA 730, 830, and 930 series. So with 1050 and 1060 and 1070 series, what they did is they placed the microchip on the front side of the on the top of the hardware board, and that too close to the processor chip, so that even with the shortest distance, I mean, they reduce the traveling distance between memory and the GPU. So even it's not much to calculate with the human eye, that the distance is not much, but the signal transmission goes much faster, which is 43% more than compared to the Maxwell GPU architecture. So here is the basic architecture of the Pascal GPU. So it consists of many transistors, like 1.7 billion transistors, previously it used to have only million transistors in Maxwell architecture. Sorry, not 1.7, 15.3 billion. So this is a Kepler architecture specifications, and these are the Maxwell architecture specifications. You can see the increase in base clock is much higher than Kepler and Maxwell. As I said before, there is no much difference between Kepler and Maxwell architectures. Only thing they did is the energy efficiency alteration. And you can see here the process size compared to 2005 Kepler and 2016 Pascal, it got reduced. So, but in 2009, 14 nanometers was used. Before Kepler, we have another micro architecture. But in 2011, till 2011 to 2016, they've introduced Maxwell and Kepler version 2. But still, they were forced to use 28 nanometer processor, which didn't give any positive results for them, and AMD took that market at the time. And speaking about another architecture, it's Turing architecture. So before talking about Turing architecture, I just want to give a brief introduction about ray tracing, which is a major feature in the Turing architecture. So ray tracing is nothing but the rendering is done like how we actually see in the real world. The lighting or the shadows which we usually see in games are not like real world lighting or shading, because then even though gaming industry used to use this ray tracing technique to develop games, but they are not implemented while officially announcing the games, because there are no hardware equipments to render the images as fast and as accurate as possible. Because while using ray tracing, to render an image, it takes almost a month, almost a day for one single image. That's complicated it is. Before gaming industries, ray tracing was used in movies for creating CGI effects and all. They are able to do that because they have high budget of cache and other hardware equipment, so they are able to render the images within a 1 year for that whole film. So to fix this problem, NVIDIA came with a architecture called Pascal architecture. So this is the architecture for Pascal, where it uses more number of cores compared to transistors compared to Pascal. It's almost at 18.5, I guess, and also the memory size is also increased. So Turing architecture basic features are RT cores, tensor cores, and we have CUDA cores. CUDA cores are also part of Pascal architecture, but they are not as effective as they are in Turing architecture. I'll explain why that is. So here you can see the architectures, all specifications previously which were used in 10 series and now which we use in 20 series. So here you can see the number of CUDA cores in Pascal architecture. It's 3584, and in the high-end Turing architecture, it's around 4352. Apart from this CUDA cores, we have RT cores and tensor cores as well. But in GTX, which they use Pascal architecture, in that we don't have any tensor cores or RT cores. These tensor cores and RT cores are specially are dedicated cores on these RTX chips, GPU chips. So CUDA cores are parallel processors, just like CPU cores. So it might be just like what we see in CPU processors, like dual core processor or CUDA quad core processors. In the same way, we have CUDA cores for GPU chips. And in tensor cores, what it does is used in AI and machine learning. Nowadays, NVIDIA GPUs are used in AI virtual world rendering, which is part of building a virtual world by tracking the traffic systems and all. So in this tensor cores, what it does is it performs the MATLAB calculations to effectively track the virtual traffic. RT cores these are the dedicated cores which are used for ray tracing, especially. I forgot to show how the ray tracing works is. 1 minute. So here is the basic image of the game without any ray tracing. Here you can see there is lighting here and here, but it's not like a real world lighting. When you switch on to RTX ray tracing mode, you can see the light is actually placed behind the wall here, exactly here, so that it can reach the floor and it can reach the wall, and it can bounce back like what we actually see through naked eye. But without ray tracing, it doesn't happen. It just the light stays there without bouncing anywhere else. I mean, it bounces, but it's not that accurate. So this is the difference between ray tracing and normal rendering. So this ray tracing process is done by RT cores here. So what it does is basically the image is rendered with.
All right, hold on a second. I got to stop you. You're at 20 minutes.
Yeah, sorry.
Yeah, you did the same thing last week. You got to set a timer and practice this stuff, because we can't go over 10 minutes, and 11 was supposed to be the limit. So why don't you wrap it up in the next like 30 seconds?
Yeah. So RT core perform this ray tracing rendering because ray tracing rendering takes much more time than what we think. As I explained before, it takes days to render one image. So what these cores are capable of performing rendering within maybe an hour or 2 hours to render one image, high quality image. Okay, that's it. Thanks. Any questions?
All right, questions?
Nope.
Yeah, I have one. Which tool do you use for raycasting? Ray tracing, sorry.
Ray tracing, ray tracing is done by the hardware equipment. I mean, it's used in software equipments like Unreal and Cinema 4D as well, but they should have third-party rendering tools like Octane Render or Redshift Render, but it's difficult to render one image in short time. It takes so much of hardware equipment and horsepower to do that. So NVIDIA came with this hardware equipment for that.
Okay. Okay, thank you.
I had one thing to answer Blade on that I should have done earlier, but Blade, from what it seems to me, as you probably already know, when we finally program quantum computers, it is a different paradigm. So I think we are going to have to think differently because of quantum circuits, and it will be a learning curve for us.
Thank you.
All right, so I think, do we just have one left? Let me look at my list again. He's gone, he's gone. I think, yes, I think Eric's it, right?
I think so.
Are you volunteering?
Isn't it more like being voluntold?
All right, whenever you're ready.
Sounds good. So, one of the things that sets us as computer scientists apart from the typical user is a desire to know how technology works so that we can make it better and
Are you sharing your screen?
That would be helpful, wouldn't it? You sure you want to see my PowerPoint?
That'd be nice.
There you go. You should see it
There
now.
we go. Yep.
All right. One of the things I think that we overlook, though, as computer scientists, though, is what the cost is of making all of these advancements. And the interesting thing for me is, the critical materials that help make our computer devices today. When we talk about computers, sometimes we think about gold or copper, things like that. But really, the thing that sets our computers apart is, well, sand. Quartz, actually, to be exact. And it's this mineral, along with rare earth elements that I'll talk about a little later, that allow for us to have these small, lightweight devices that we've been talking about all night. When we talk about, there we go. When we talk about quartz, it's really a structure that's made up of two elements. Quartz is silicon with two oxygen molecules attached to it. And when it's mined from the earth, it gets crushed into sand. And it's important to note that the structure of this sand is specific for the silicon we use for computers. For example, like we can't just go out to the Sahara, right, and just gather up buckets and buckets of sand and then have, all the processors we want, because desert sand becomes too round with the way that its structure is built. Quartz, on the other hand, has an elongated structure, which makes it more stable, easier to refine, and easier to remove other impurities that sometimes get intermixed as the rock layers formed. And it's these impurities that are kind of intriguing, because the way that we purify this silicon to turn it into a silicon ignite like this is we add reagents to it that make them hydrophobic, meaning that they repel against water. So that when we drain off, or when we mix it with water and then drain that water off, what we get left is just pure quartz, which is really important, because in order for us to have the silicon we need to make the chipsets we've been talking about with the graphics cards and the processors, and honestly, even some of the quantum stuff, is it has to be 99.99999999999% pure. Right? That's 99 with 11 nines attached to it, in order for us to have the right level of purity in order to be able to make the silicon that we need to make the processors that we need. Now, we're still talking about quartz here, right? In order to get to the silicon levels that we need, we have to heat it up to extremely high temperatures. And this is kind of what you can see here, right? You have the ore here on the left-hand side. In the center, this is a raw ignite. And what happens here is there's a silicon seed that's used, which is this point here. And the rest of the silicon just lines up behind it as it gets spun away. When it gets heated to extremely high temperatures, the oxygen flies off of the silicon, giving us just this pure, almost 100% pure ignite. And then we polish it, slice it up into thin pieces. And then we get to that little fun part that Seth was alluding to, and we were hearing about in our last presentation too, with this idea of transistors. Just to give us an idea or a baseline, I want to show you just a quick video in order to talk about where we're going with this transistor idea.
Modern computers are revolutionizing our lives, performing tasks unimaginable only decades ago. This was made possible by a long series of innovations, but there's one foundational invention that almost everything else relies upon: the transistor. So what is that, and how does such a device enable all the amazing things computers can do? Well, at their core, all computers are just what the name implies: machines that perform mathematical operations. The earliest computers were manual counting devices, like the abacus, while later ones used mechanical parts. What made them computers was having a way to represent numbers and a system for manipulating them. Electronic computers work the same way, but instead of physical arrangements, the numbers are represented by electric voltages. Most such computers use a type of math called Boolean logic that has only two possible values: the logical conditions true and false, denoted by binary digits 1 and 0. They are represented by high and low voltages. Equations are implemented via logic gate circuits that produce an output of 1 or 0 based on whether the inputs satisfy a certain logical statement. These circuits perform three fundamental logical operations: conjunction, disjunction, and negation. The way conjunction works is an AND gate provides a high voltage output only if it receives two high voltage inputs, and the other gates work by similar principles. Circuits can be combined to perform complex operations like addition and subtraction, and computer programs consist of instructions for electronically performing these operations. This kind of system needs a reliable and accurate method for controlling electric current. Early electronic computers like the ENIAC used a device called the vacuum tube. Its early form, the diode, consisted of two electrodes in an evacuated glass container. Applying a voltage to the cathode makes it heat up and release electrons. If the anode is at a slightly higher positive potential, the electrons are attracted to it, completing the circuit. This unidirectional current flow could be controlled by varying the voltage to the cathode, which makes it release more or less electrons. The next stage was the triode, which uses a third electrode called the grid. This is a wire screen between the cathode and anode through which electrons could pass. Varying its voltage makes it either repel or attract the electrons emitted by the cathode, thus enabling fast current switching. The ability to amplify signals also made the triode crucial for radio and long-distance communication. But despite these advancements, vacuum tubes were unreliable and bulky. With 18,000 triodes, ENIAC was nearly the size of a tennis court and weighed 30 tons. Tubes failed every other day, and in 1 hour, it consumed the amount of electricity used by 15 homes in a day. The solution was the transistor. Instead of electrodes, it uses a semiconductor like silicon, treated with different elements to create an electron-emitting N-type and an electron-absorbing P-type. These are arranged in 3 alternating layers, with a terminal at each: the emitter, the base, and the collector. In this typical NPN transistor, due to certain phenomena at the PN interface, a special region called a PN junction forms between the emitter and base. It only conducts electricity when a voltage exceeding a certain threshold is applied. Otherwise, it remains switched off. In this way, small variations in the input voltage can be used to quickly switch between high and low output currents. The advantage of the transistor lies in its efficiency and compactness. Because they don't require heating, they're more durable and use less power. ENIAC's functionality can now be surpassed by a single fingernail-sized microchip containing billions of transistors. At trillions of calculations per second, today's computers may seem like they're performing miracles. But underneath it all, each individual operation is still as simple as the flick of a switch.
So when we take a look at this idea of the central processing units for home computers, right, you can see, right here at the top, right, the first commercially available home processor was the 8080. And the thing I find interesting about it is it had 6,000 transistors embedded in it, which gave it a clock speed of 2 megahertz, right? You can see it's 6 microns wide. But the thing that I find really fascinating about this is that as we walk our way down this list, right, this smallest wire micron size gives you an idea of how big the chipsets are, right? You can see we get constantly smaller. As we get smaller down here at the bottom, you'll notice that our transistors are constantly going up and up and up. What this does, and the data I was able to find accurate information on, stops at 2004, because once we get past the 2004 mark with the Prescott series of the Pentium, things get difficult because we moved into multi-core computing. For example, right, when we take a look at what's going on today, the i9-9900K, which is last year's model, it was an 8-core processor, but it had 1.736 billion transistors spread out throughout all of those cores. So again, we're keeping up with this idea of we make things smaller, we add more transistors. More transistors means we get more things done. Now, will we ever get to the level of the quantum computing? No, but the idea is there, right? Smaller CPUs, more transistors, more instructions can happen. One of the other things I find really interesting too is when you take a look at where all of this quartz that I've been talking about comes from, it all actually comes from one spot, Spruce Pines, North Carolina. Because in the foothills of the Appalachian Mountains here, we have the purest natural quartz deposit in the world, which cuts off the refining costs, makes it more cost effective. Now, the interesting thing is, based off the research that I was reading, no one's freaking out that we're using up all of our quartz yet, but that could potentially be an issue moving forward based off of a phenomenon I'm going to talk about here in a second. Associated with all of this quartz and sand ideas is what we call rare earth minerals. And you can see some of the samples there in the slide, as well as what they're used for, right? Rare earth minerals are all over the things that we use, whether they be LCD TVs, rechargeable batteries, cars, petroleum refinery, vehicles, etc. But all of these rare earth metals, unlike their name suggests, are actually common. The challenge that we have is being able to mine and refine them, getting the quantities that we need. And here's something that I found really interesting. So if you think about the cell phone that we all carry around, right, in order to build that cell phone, we need approximately 1 gram of rare earth elements. Right? In order to get 1 gram of rare earth elements, we need 52 grams of ore, of rare earth ore mined from the ground in order to make that. Now, if you scale that and think about how there's estimates around 6.8 billion cell phones in the world, right? What you end up with is about 390,000 tons of ore required just to build the cell phones that we use. How does that translate to size? Well, to give you an estimate, that's the equivalent of 5 United States aircraft carriers. That's just for the cell phones, right? And keep in mind, these are some of the biggest ships we have. I mean, here's a person down here, right? This is a Nimitz aircraft carrier. We're taking 5 of them, stacking them together. That's how much ore we need in order to process just the cell phones in the world, not including monitors, not including CPUs, not including any of the other things that we use. The interesting thing that I found with that too is that this becomes really important when we take a look at where it's coming from, because the rare earth metals that we use don't actually come from the United States, but they come from overseas. They come from impoverished places that have little restrictions, lots of crime, and they're using mining processes that cause huge environmental impacts, things that the United States has outlawed and regulated in order to get all of the metals that we need. So when it comes to taking a look at the magnificence of technology that we have today, it's important to think about and remember that sand, one of the most prolific minerals that we have on Earth, is the thing that's responsible for almost everything we use. From the computers that we work on, to the buildings that we exist in, to the roads that we drive on, even the vehicles that we use, right? None of it is possible without this idea of sand. But furthermore, the technology that we use for speakers and screens and circuits all come from even more minerals. While talking about this, I'm not trying to be an alarmist, but I want to point out the fact that even though we still have plenty of these resources, as Christian computer scientists, we should be aware of where it is that our things are coming from as we seek to be stewards of the earth that God's given us. Questions?
Any questions? I like that last part with the connection of where the actual stuff comes from, and that's something we rarely actually think about, right?
Absolutely.
You know, we're just consumers of everything, and we don't really care where it comes from as long as that makes our life better.
I really like the video. I appreciate TED Eds. Those are fun.
Yeah.
Anything else? All right. So let's see. So that's everybody here. So the next time we will meet is via Zoom 2 weeks from today. I guess everybody get up to their computer with their Arduinos and can clear out a nice space on your counter. I mean, like usual, if you want to do it on your own, you can, but I'd still encourage you to get together as a group, and that way you can help debug things and stuff like that. So I'm around for all next week and things like that. So if you, I think, what's our next research topic?
Software engineering.
Okay, but that's not for 3 weeks, right? Is that accurate? Let's look.
April 16th. So.
Okay. So potentially that could be back live if the university opens back up.
Hey, that'd be nice.
So yeah, so in any case, 2 weeks from today, we'll meet for embedded systems, all the same room. I'll be here. Bring your Arduinos and you know, whatever, and we'll get through that. If you start working on your research and you have questions, I'm around. The cruise got canceled, so but I made out pretty well on that whole thing. By holding out and not canceling, I got a 225% credit. So I got 2.25 cruises for the price of one.
Nice.
Whoa.
Yeah, I know, so good. So that's the scoop. So I'll upload this recording if you want to go back and rewatch the stuff. I'll communicate with Alexis as well, since I had originally told her next week, but we're not actually meeting for 2 weeks. So plan on the very beginning of our next meeting to have a presentation from her, and then we'll move over to the embedded systems. Sound
And what
good?
about the midterm?
Midterm, that's a good question. That's on embedded systems, isn't it?
It was Maddie.
Yeah, it's not going to be anything over.
Maddie, no.
It was Maddie.
It's not going to be anything over presentations, anyways. Let me figure that out. It'll be something with embedded systems, but I'll message something. It won't be, the earliest it'll be due is, I don't know, like 3 weeks from now or something like that. Just to burn some time, we'll figure it out. Or we'll just double up on the final and it'll just be embedded systems. Sound good?
Sure.
We'll figure it out. All
Cancel
right.
it like all of the United States.
Yeah. That's kind of playing catch up with everything. But, you know, the hope is that in a month, we're all back at school and we say, oh, well, we overreacted, but, you know, better safe than sorry. Instead of, had they not done this, we would have been, you know, possibly things would have gotten way, way worse. Like, I think they might get way, way worse, and then we regret not taking all the precautions. But you still shouldn't put hand washing things at the end of your presentations. It's garbage.
Why? Shots fired.
What?
Shots fired.
So Eric, what is Sheboygan Lutheran doing? Do they have any special thingies?
Not right now. We've been told to think about what we might have to do if we go online, but yeah, I'm not looking forward to that. I've been having discussions with some of the other tech guys in the county area, some of the other public school districts, and their admin teams are telling them to look at cellular hotspots and stuff like that. And I'm like, oh my goodness, this is going to be just a big mess.
I see. Yeah,
Minnesota, there's rumors that in Minnesota they're going to do that. It's not technology yet, but my mom just texted me and said they're probably going to cancel all the schools there.
Yeah, see, it's interesting because Maddie had said that Acuity really hasn't done anything major with it either. I wonder, is that location based? Like Sheboygan, they figure it's not as densely populated, so they don't need to freak out, or is it more of just a Sheboygan mentality?
To me, it feels like everybody's in a Mexican standoff. We're just waiting for somebody else to pull the trigger so we can be like, those guys.
Yeah.
I think that's kind of what happened with Concordia. As soon as UWM
right, that's what I figured.
Did it, then they just, everything hit the roof.
You couldn't look like the school who didn't care.
Well, yeah, and I don't think we should. So, I mean, I think they made the right call. The hope is that we look back on it and say it was a waste of time, but still the right call.
Agreed. There was a guy who showed up, the janitor walked into my office today and started wiping things off with bleach.
Yeah.
Oh.
Because I'd much rather look back on this and joke about it that it was a waste of time that we did this than have it get way, way worse. Like it legitimately could, and who knows. But, you know, we'll hold down the fort, and I'll be on campus the rest of this week, and I'll probably be in and out next week, but I'm around. So if you have questions about your research stuff, if you happen to start it early, feel free.
Sounds good. Thank you.
All right. Yep. See everybody in a couple weeks.
Good night, everyone.
Bye.
Bye-bye.
See ya.